Good morning. Can I test that you can hear me? Good morning. Can I test that you can hear me?
Oh, who's this? Sorry.
Hey, Lek. Yes, we hear you very well.
Hi. Hello. I'm the speaker for the next session. Good. So you can hear and see me.
Yes, yes.
Oh, I see.
Who
Well,
is the it's-
well, welcome to the session. We have just left it on so I can join.
Fantastic. Excellent.
Yeah. So, uh, well, probably I didn't check the list. So you'll be talking about JWST and planetary things. Okay, good.
Yep, that's right. Let me just see if we can share my screen, shall we?
Oh, sure. Yes, I can see it.
So can you confirm that that's visible on the screen?
Just change the slide so I can tell it's moving okay.
There we go. Moving between the two.
Oh, yes.
So yeah, Lek, so we see your presentation, so we will be starting in 2 minutes.
Okay, I'll stand by and wait for you.
Okay, so you're attending virtually, right?
Yes, that's right.
I see. Well, this is Sultana Nahar from the Ohio State University.
Ah, hello. Okay, so you're also attending virtually, are you?
Yes.
Right.
All right. So, well, I will wait for your talk.
Fantastic.
Okay, nice to meet you.
Okay. Oh, okay. Good morning, everyone. So welcome to the third day of the Symposium 393 about planetary science, exoplanets and planetary science in the era of James Webb Space Telescope. So we will kick off our session today with the first invited speaker, Lek Fletcher, who will be talking about GWST, a new explorer for giant planet system. So Lek, the floor is yours.
Okay, thank you very much, everybody, and thanks to the organisers for inviting me to give this talk today. So I have the privilege of presenting to you the work of several teams working on giant planet observations from JWST, and I want to acknowledge the fact that this would not have been possible without the work of Heidi Hamel. Heidi put together a small consortium of experts working on planetary exploration and offered to give up some of her rather valuable time so that we might use this facility to look at various objects in the solar system during the first cycle of observations, a real test of this new facility to see what it could do and also to get some exquisite new science out of it. I also want to acknowledge Imke de Pater and Thierry Fouché, who led a dedicated program looking at the Jovian system, and the army of postdocs and PhD students who have been poring over this data for the last couple of years, trying to extract as much science as possible. Without them, none of the slides that I'm presenting to you would have come to fruition. So this will be a whistle-stop tour of some of the latest results that we have for the giant planet systems, Jupiter, Saturn, Uranus, and Neptune. And I'll start by actually staying on that first slide. Here you can see all the program numbers that have been dedicated to the giant planets so far, both the planets themselves, their rings, and their satellites. You can see both guaranteed time observations at the beginning, early release science dedicated to Jupiter, and since then, guest observer program observations for the first 3 cycles looking at these giants. So why would we be interested in exploring these giant planet systems? First off, these planets are so massive that they contain within them the fingerprints of their formation, a way of looking back at the composition of the protosolar nebula when the planets were first forming billions of years ago by measuring the chemical composition of their bulk. They are huge natural scale laboratories for studying the physics underpinning atmospheres and ocean dynamics and the flow of material from place to place. They can be used as a sort of mirror for understanding the processes at work in the wider magnetospheres of these systems, and they harbor potentially habitable ocean worlds orbiting around them. A chemical inventory of those ocean worlds, I know, was a topic that you covered yesterday with several presentations and talks. Now, there's a huge wealth of information in these data sets so far. So a lot of it has not yet been published. And if that's the case, you'll see a little no sharing icon turning up in the top right-hand corner of my slides. But several results have come out, so I'll take you on a bit of a tour of those so far. Now, of course, we know that JWST was built as a machine designed to look at the most distant objects in the universe, to probe the very dawns of our universe's existence. And so to point this exquisite observatory at some of the brightest objects nearby, particularly in our solar system, was seen as a little bit of a risk in the early days. But when we do zoom in on some of these pearls that wander into those fields of view when our colleagues are looking at distant galaxies, reveals the power of this observatory. These are the first images of Neptune that were acquired by the observatory back in June of 2022. And these had tears in our eyes when we first saw these observations, because you're seeing objects and features within the Neptunian system which haven't really been observed since the Voyager flybys of the 1980s. Back in the 80s, we had Voyager flying by Jupiter, Saturn, Uranus, and Neptune in a golden decade when these worlds were really revealed to us for the first time. And now today with JWST, we have a new opportunity for comparative planetology that we simply haven't had for the last 30 years or more. So you can see the rings of Neptune just there, the various satellites that are orbiting around those rings, and incredible detail of the powerful atmospheric physics at work within Neptune's atmosphere. More on that a little bit later on. Closer to home, we have some stunning images from NIRCam of the Jovian system. So Jupiter, of course, has been observed over many years with visiting spacecraft and observatories, including the Juno spacecraft, which is currently orbiting around Jupiter. But JWST does give us a new window into the Jovian atmosphere by sounding wavelengths that are simply inaccessible from Earth, inaccessible from Juno, or they're simply too dark for us to really reveal any contrasts in any previous facilities. Now, of course, Jupiter is big, it's bright, it's moving, and it's rotating. It overfills the field of view. So it was always going to be a challenge for JWST. And indeed, one of the consequences of observing Jupiter is that we've been successfully teasing the astronomical community ever since. When we observe Jupiter, there are persistent issues on the NIRCam detectors, and so my colleagues in stellar astrophysics and cosmology and galactic astronomy were quite concerned when they were seeing Jupiter in several of their images for many hours after we had observed the giant planet itself. So on behalf of the Jupiter community, we apologize to our astronomer friends for any challenges they faced. Of course, this is not a long-term issue. It does no harm to JWST, and I want to assure you it allows us to do some absolutely fantastic science. So my colleague Ricardo Hueso over at the University of Bilbao was working with the early release science team and analyzing these observations of Jupiter at several different wavelengths. As I mentioned, the wavelengths accessible to JWST are those that we really haven't had the capability for in the past, including this very deep methane and hydrogen band near 2.1 microns that allows us to see little tiny cloud features at the equator at higher altitudes than we've ever probed before. Now just think, we've been observing Jupiter for 40 years and tracking the winds by monitoring how these clouds move around. By seeing clouds that we haven't had access to before, we're measuring the winds in a completely different realm of the atmosphere, higher up above the main cloud decks. And out from the data very quickly popped a brand new equatorial jet high over the equatorial atmosphere that had not been spotted. It had been hidden in 40 years of data previous to that. We now think that that jet might be associated with oscillation patterns high in the stratosphere, and it could be thought of as like an equatorial heartbeat for the Jovian atmosphere, analogous to the quasi-biennial oscillation that we have here in the Earth's atmosphere. The only way we'll find out more is by more monitoring with JWST over the years to come. Now, that's one result that comes from imaging from JWST, but I would argue that the real superpower of this facility is the ability to take spectroscopy. And we designed the guaranteed time program to try and acquire spectra of all 4 of the giant planets and their satellite systems. On the left-hand side here, you can see a montage of averages of the data that we've been able to acquire so far. This spans from a realm where reflected sunlight is dominating. So you've got light from the sun being reflected from the gases and aerosols within the atmosphere. And those gases can then eat away at the light in certain bands to create these deep absorption features. That broadly is everything left of about 4 to 5 microns. Then beyond 5 microns, what you're seeing is thermal emission. So you're seeing a continuum of hydrogen and helium, the bulk of these planets made up of those 2 gases, with absorption and emission features from various species sat above them. What we can do is we can read and model these spectra to then analyze the structure of these atmospheres in 3 dimensions to back out the thermal structure, the distribution of clouds and aerosols, and the distribution of chemical species to tell us not only about the chemistry, but also about the dynamic motions moving these things from place to place. So I'll show you some of the results that are coming out of that spectroscopic survey. Here's a montage of observations of the most famous storm in the solar system, the Great Red Spot, taken by a 2x3 mosaic of near-spec observations focused on the GRS itself. You can see top left, reflected sunlight from aerosols high over the Great Red Spot. Bottom right, you can see thermal emission from the cloud-free regions surrounding the Great Red Spot, which is why the spot itself appears black here, because it's blocking all the light emanating from below. Bottom left, you can see reflection from the cloud tops themselves. But the interesting one from my perspective is what you can see in the top right, which is in a region which is usually too dark to observe, even with spacecraft like Juno and Cassini before that. And interestingly, within the Great Red Spot itself, you can see internal structure. You can see oval-like shapes that we haven't really been able to get access to before. That's intriguing because there are different theories about the stability of this storm. The storm has been shrinking over the last 40 years or so, and the question is how long it will persist for. Fundamentally, if this is a cylinder that extends down into the deep atmosphere, models suggest that that is an unstable configuration. And we're more likely to have stability if we have a kind of ice cream cone-like shape, like the one on the right-hand side, tapered at the top and tapered at the bottom. The fact that we are now seeing structure, oval-like internal structure at the top of the vortex on the top right-hand side argues that we have a more stable configuration maybe than previous models have suggested. Higher above the Great Red Spot than those observations, there was a study a few years ago that suggested that waves emanating upwards from the weather layer, from the troposphere, was heating the ionosphere and causing it to glow. Those acoustic waves had not been previously detected, but we were intrigued to go back and look again. JWST has the capability to do that using the H3 plus ion, which is a way of probing the temperature and density of the ionosphere. And lo and behold, we see no evidence of heating from the Great Red Spot whatsoever. Somewhat of a disappointment until we looked more closely. In the image on the right-hand side, you can see a plethora of structure which look like periodic wave features we believe to be waves in the low latitude ionosphere of Jupiter that are maybe forced by activity such as storm systems below, but certainly a new window onto the dynamics of the ionosphere that we've simply never had before. That was work published by Henrik Mellin earlier this year. Back down into the deeper atmosphere, we have the ability to measure the three-dimensional temperature structure of the atmosphere, which we're doing with those are three-color images on the left-hand side, taken over 2 epochs in 2022, showing the internal thermal structure of the vortex. We can compare that to both Hubble and JWST observations to connect the winds that are measured by JWST and Hubble to the thermal structure that we can then derive. And that's work that's been done by a PhD student, Jake Harkett, that's hopefully going through review at the current time. So moving from Jupiter out into the more distant solar system, but staying with the theme of spectroscopy as the superpower of JWST. The movie that's now playing on the right-hand side is our observations of Neptune, spanning from reflected sunlight, where you'll see some enormous gargantuan methane cloud structures glowing in reflected light and varying over short timescales on the disk. And then as we get out into longer wavelengths, you'll see the warm equator and warm polar structure, the polar vortex enhanced in chemicals such as hydrocarbons, suggesting a large-scale circulation pattern within the Neptunian system. We have multiple epochs of Neptune data supported by the Hubble Space Telescope and the Keck telescope on Earth. So we have a wonderful Neptunian data set that we're still working on at the moment. Now, blink and you will have missed it in that movie, but at 3 microns, we also have the capability to look for ionospheric emission, again from that H3 plus molecule. Now, all of the giant planets are expected to have H3 plus, and indeed it has been detected on Jupiter, Saturn, and Uranus in the past from the splitting of hydrogen into its component parts and the reformation of this H3 plus ion. Now, weirdly, despite looking with ground-based facilities for many years, we have never detected H3 plus on Neptune before. We were unsure why. Maybe there was some process that was scavenging and removing this ion within the Neptunian atmosphere. It turned out you just needed a $10 billion extremely sensitive space telescope to be able to detect it, because it quite literally leapt out of the data when we first looked for it. We had to do some processing. We had to remove all the reflectivities from the very powerful, from the very spectacular clouds that you can see in the top row of this image. But once we did that, we could start mapping out the emission from this H3 plus molecule. Not only have we detected it for the very first time, but the locations of the greatest emission maps to the expected latitudes of the Neptunian auroras. So straight away, we have a new window on studying the auroras and the magnetosphere of Neptune that we've never had before. Furthermore, there was a good reason why no ground-based telescope had detected this emission. It turns out that the thermosphere of Neptune is much cooler by hundreds of Kelvin today than it was back in 1989 when the Voyager spacecraft flew by. As you cool down the thermosphere, you reduce the emission by orders of magnitude. So again, you needed JWST in order to take these new data. Moving now to Uranus, and again, here's a stunning NIRCam compilation of Uranus, its classical 5 major satellites and its rings. But it's spectroscopy where the real action is at. This is a montage of observations from the NIRSpec instrument, from about 1.7 out to roughly 5.5 microns. Again, you're seeing reflected sunlight here with methane and deuterated methane eating away at that reflected sunlight. But you're also seeing fluorescence and non-LTE emission from things like carbon monoxide, from H3 plus again, and from carbon dioxide. Now, we can simulate these data, and there's a paper that's being prepared by Michael Roman at the University of Leicester right now, which fits these data and measures the cloud properties of the Uranian atmosphere. And you can see a polar projection of the north polar cap that has formed over the last several years as Uranus's north pole is swinging into view from the perspective of Earth and the Sun. And as it does so, you get this intriguing chemistry and aerosol microphysics, which produces a reflective cap of polar aerosols over the summer and springtime poles of Uranus. Moving to longer wavelengths, this is what really got us excited, because at longer wavelengths, Uranus simply hasn't been seen in anything like the detail I'm showing you on the screen right now. We had some crude observations out at 17 to 20 microns taken by the Very Large Telescope. And we had a rather grainy and difficult image at 13 microns, sensitive to acetylene emission that took several hours of integration to acquire. In just 10 minutes of observations, we not only exceeded that, but also gave access to some wavelengths, such as the methane image on the bottom left, the ethane C2H6 image in the center at 12.3 microns, that nobody has seen before. The structure you see there is giving us access to the stratospheric temperature gradients. It's telling us about large-scale overturning circulation high up in the Uranian stratosphere, which, as I mentioned, has not been accessible before. So we have a paper that is currently in preparation that's looking at the temperature, the chemistry of the atmosphere, detecting new molecules down in the rather darker regions of the spectrum. But this is where JWST does reach its limit. Look out there at 6 to 7 microns on the far left-hand side. The gray is actually the background. The purple is the spectrum that we have measured. So we are still background limited just here, and we do not detect photons from Uranus between 6 and 7 microns, except in very narrow emission features that are associated with water within the stratosphere of this planet. So there's still challenges to overcome, and maybe if we build up more data, we'll be able to answer those challenges. If we do polar projections of the NIRSPEC data on the left-hand side, and our new MIRI data on the right-hand side, you can see how these things are all connected. That's the polar aerosol cap on the left-hand side that I showed you previously. Now, for the first time, we have structure in the stratospheric methane distribution and the tropospheric temperature distribution, revealing a warm polar cyclone at the North Pole of Uranus, and these concentric rings of methane emission around the pole that we're still struggling to understand, but give us a suggestion that there are large-scale overturning circulation patterns going on just there. And finally, H3 plus at Uranus has also been intriguing. When we use the 3 longitudes that we observed, we're able to observe for the first time the auroras in H3 plus emission. There has been some tentative detections of those in the past, and they've certainly been observed in the ultraviolet, but here they are quite obviously showing up in H3 plus emission just there. But that's not the most exciting thing about the Uranian ionosphere observations. If you look right at the pole, you might see between these 3 snapshots weird V-shaped structures in the ionosphere over the polar domain. We simply don't understand what they are. They might be related to the density structures within the Uranian ionosphere and its weird magnetic field that's caused by its multipolar magnetic field shape. But we're still diagnosing and trying to understand what we're seeing in these data, a new window into the Uranian ionosphere. Moving back in the solar system again, Saturn has been observed by the MIRI instrument. We put 3 footprints from the equator up to the North Pole to capture the environmental conditions during northern summer times. Cassini, of course, observed from southern summertime through to the northern summer solstice when the North Pole was directly in view from Earth. Now, if you look through a telescope at Saturn, the rings are almost completely closed up as the equinox is going to take place early next year. And so the question was, can we compare the conditions that JWST sees to those that Cassini observed 5 or 6 years earlier on? I wanted to showcase the exquisite quality of the spectra that we're getting right-hand side just here. So I've taken a spectrum from the North Polar region in red and from the equatorial region in blue. And believe it or not, the data are the tiny little dots with error bars, and our model is the black line. So we're capable of reproducing the spectra of Saturn using our simulator called Nemesis in order to fit for temperature, for composition, and for aerosol structure. And if you do that, you start probing this atmosphere in 3 dimensions. You can measure the distribution of temperatures with latitude on the x-axis and pressure on the y-axis, showing you a large-scale oscillation pattern over the equator that we knew to exist. And there's the hot North Polar cyclone, which is a seasonal polar vortex. We expect that to dissipate over the next few years, to break up as waves start to oscillate around the polar vortex and take away the contrast that we can see at the present time. So it's an extremely dynamic atmosphere. But the thing that really got us intrigued in the new JWST data was the fact that we could compare the large-scale circulation patterns of Saturn compared to what Cassini observed back in the southern summertime conditions. Now, this is a cartoon by Deborah Bardet over in Paris, which shows the equatorial oscillation, and it shows the large-scale motion of the stratospheric air from southern summer latitudes to the north, back in southern summertime conditions. But now with JWST, that huge circulation, planetary scale circulation pattern had completely reversed. We were getting rising motion in the north, sinking motion in the south, and we could detect that by using the various gaseous molecules here as tracers of that motion. So plenty more that we can still do for the atmosphere, but that wasn't the only thing we looked at in the Saturnian system. We also took spectra and images of the small satellites, some of those not really well studied by the Cassini spacecraft due to its great distance, and of the Saturnian rings. I'm just going to focus on what's going on the bottom of this slide, because I really like this as a demonstration of the transition from reflected sunlight below about 8 microns out to thermal emission. So with reflected sunlight, the A and the B ring, which are highly crystalline, they're very reflective, they're showing up really brightly in the MIRI data. But as soon as you get out beyond about 8 or 9 microns, you switch into a thermal regime where the brightest colors here are now the warmest temperatures. And here you see that the C ring and the darker material in the Cassini division is simply physically warmer and therefore glowing. So you transition in this little movie from reflected sunlight, where the reflective stuff is brighter, out into thermal emission, where the warmer stuff is brighter. And I really like that as a demonstration of what JWST is able to do. Now, I wanted to start to conclude now by acknowledging the incredible work that's being done for the Galilean satellites and the rest of the satellites in the outer solar system. I know this was touched upon at length yesterday, so I'll briefly summarize here. We've been able to look at the volcanic emissions, including sulfur monoxide emission over various volcanic vents on Io. We've been able to look at the carbon chemistry and the potential internal sources of carbon on this incredible moon Europa. We've looked at the distribution of species, including hydrogen peroxide on Ganymede, showing how it's connected to the interaction with the magnetic fields within the Jovian system, localizing H2O2 over the polar domains. And Richard Cartwright and colleagues have done incredible work looking at the structure of Callisto, detecting a carbon dioxide atmosphere and studying the distribution of carbon-rich species across the surface. So lots that can be done there. And actually, over the course of the next few years, I think you're going to see a movement into starting to compare the icy and mineral structures across the surfaces of each of these features. We've got Europa, Ganymede, Callisto, Enceladus, and Triton all compared here, with several of the more interesting ice species that have been detected so far labeled. But of course, with the scale on the y-axis on this diagram, I'm hiding a tremendous amount of structure and gaseous emission lines and small dips at the 1% level that might be signatures of exciting organics and hydrocarbons on the surfaces of these potentially habitable ocean worlds. So watch this space for lots of really cool science that's going to come out of that field in the next few years. But I want to take a step back and mention some of the incredible work that needs to be done before we can publish all of these data sets. It's not been easy to get used to this brand new facility and the various nuances and tricks that we need in order to analyze these data. I'll give you 3 examples. So the wavelength calibration of the MIRI instrument, when we first started analyzing it, was a fair way off. It wasn't matching up to any of our atmospheric models. And so we had to go spend months really of going through and tweaking the wavelength calibration of MIRI MRS in order to match the Jupiter and Saturnian spectra. Now, these were great targets to look at because they're so rich in gaseous emission features that we understand we can match really well. And so if you are using MIRI MRS right now, you are using a wavelength solution that has been created simply by looking at Jupiter and Saturn with the guaranteed time observations. We also have a technique that now fixes saturation within the data. Of course, we can't recover things that are right at the limit of saturation, but you can see on the right-hand side that where things like Jupiter and Saturn are saturating in 2 or 3 groups on the planet, we can now use the pipeline in order to extract that data and reconstruct it. And we noticed that with the IFUs, as fabulous as they are, they did create a lot of weird artifacts, structure across the IFU field that we had to account for. Thankfully, because we dithered each of these observations, we always had 4 dithers for every single observation. We could identify self-similar structure within those dithers and develop an algorithm for creating a map of that structure and then subtract it from the data. And you can see how successful that has been by looking at the images of Saturn on the right-hand side just there. And I urge you to take a look at that citation if you'd like more details. We've also developed a custom piece of code in order to map planetary observations. This interfaces with SPICE kernels directly, but the thing we like about this is it's quite easy to install via pip. It's a Python package. It does not require any coding capabilities. You can download this onto your laptop, and you can then map any planetary observation, provided you have the details of exactly the moment in time in which it was taken, in order to create maps, to analyze the data. So you can see in this little movie here how we use it to fit the limb to try and exactly match what we're looking at. Then you can add things like the rings of the Neptune system in here. You can add in, if you want to, various satellites that we know to be present within this particular field. So if you see a bright dot in your image and you're not quite sure what it is, you can use Planet Mapper to identify that quite readily. You can, of course, change all the colors and bits and pieces and mess around with the contrast within these images. And crucially, at the end of this process, you can turn it into a map that can then go on for further analysis of the features that you are seeing. So Planet Mapper is available. It's published by Oliver King, a Leicester postdoc, and he is maintaining it. Please go ahead and use it for your work. And finally, I wanted to highlight that Cycle 4 is just around the corner. Solar system science gets about 5% in the time allocation. And of course, there was this enormous 9-to-1 oversubscription on observing time last time. That typically means that solar system observations are in the small category, the less than 25 hours category, at least as it was for Cycle 3 and before. The bottom line here is that if we don't keep up the proposal pressure from solar system scientists, then we will start to lose that slice of the pie. So let's keep, as a community, pushing our great ideas into the JWST TAC, despite this rather terrifying oversubscription, and we'll keep this program of outer solar system observations going. So my final slide, to summarize, we've had a fantastic couple of years of science from JWST so far, and I really do hope that this is the start of a long-term, maybe 20-year program of studying the atmospheres of the seasonal and non-seasonal giant planets over large swathes of time. I'm sure there's plenty more exciting science still to come out of this data set. And once again, I want to acknowledge the huge efforts of the postdocs and students and members of the research team for doing all of this incredible work. So with that, thank you for your attention, and I'll pass it back to the auditorium.
Oh, thank you very much, Leek, for your nice presentation and showing what's the wonderful science that we can do with JWST for the solar system planet and for the solar system science in general. So now we have time for questions. So for those who are online, so please also type your questions in. We will bring them to the speaker. So yes.
Yes, good morning, Lee. Thanks for a beautiful talk. This is Evine van Dishoek from Leiden. Beautiful spectra also. I was wondering, I understand the analysis is still ongoing, but for Uranus and Neptune, can you give any indications whether you see enhanced abundances due to inflow of icy planetesimals, or do you just see the high temperature atmospheric chemistry going on?
Yeah, it's a good question. So the way in which we'd be able to detect that would be using water emission features. And we have been able to map those water emission features over Uranus to begin with. Neptune, it's been a little bit more tricky because of its size. I have to say that the distribution of water across Uranus seems to be relatively flat, at least as far as we can tell right now. That's not to argue against the infall of material. It just suggests that it's coming in from all directions equally rather than being localized over, say, the equator or the pole. That's going to be part of this publication that we're working on. But for Neptune, it's quite tricky because with near spec, we still only have a handful of pixels across the field of view, and we have to deal with light being scattered outside of the field of view as well. So I'm not sure we're going to be able to answer that question for Neptune, but for Uranus, we should be able to.
Great. Any more questions in the room? So if not, let's thank our speaker again.
Thank you, everybody. Enjoy the rest of your day.
Thank you very much. And now we'll move to the next speaker, which is going to be Wayne van de Jock. She will be talking about probing the gas that spoiled planets, a result from James Webb Mines disk program.
Good morning, everybody. Thanks for coming here on this final day. I'm going to take you out of the solar system again. We are going to talk not just about planets, but about forming planets, especially the disks that are actually producing these planets and probing the gas in those disks in the inner regions where the giant and terrestrial planets are forming. And this is results from our guaranteed time program with the MIRI instrument called MINDS. So we've heard already and seen quite some spectroscopy, but I thought that maybe this audience is not so familiar with spectroscopy. And since I'm an astrochemist, we of course have more than just JWST to look at chemistry. We have ALMA, which is a fantastic astrochemistry machine. There we're actually looking at the rotational lines of the molecules. With JWST, we're looking at the infrared, at the vibration transitions, and there we have both stretching modes and we have bending modes, here in this case of the water molecule. Now, the information that we get is actually quite complementary. With ALMA, we actually observe both simple but also complex gas phase molecules at exquisite spectral resolution, resolving powers of 10 to the 7, and that also allows us to go down to very low abundances with respect to hydrogen. With the infrared, we have usually lower spectral resolving power. In the case of JWST, typically 3000. But we can uniquely probe symmetric molecules that don't have a dipole moment, permanent dipole moment that you need in order to see them with ALMA. We can also see both gas and ice, but we can only do it down to abundances of about 10⁻8. So we're probing the major reservoirs of carbon, nitrogen, and oxygen. I'll be talking here uniquely about the gas, not all about the ices. So here we have a planet-forming disk, usually structured. We now know that thanks to ALMA, and ALMA observes that structure in the disks and also some of the gas that is in the outer part of the disk. For example, with the MAPS program led by Karen Oeberg. With JWST, we're probing the warm gas that is actually in the inner part of the disk, typically in the inner few astronomical units. We can also look at the ices if you have an edge-on situation, but I will not be talking about that here today. Now, for those of you that are not so familiar with spectroscopy, here's sort of spectroscopy 101. Here is your carbon monoxide molecule at 500 Kelvin, beautiful R and P branch lines that you see there. But every molecule has its unique pattern. CO2, for example, has not just R and P branch lines, but also a Q branch. And that Q branch you can actually see quite easily, even though probably most of the information is in the P and the R branches. And then you have a beast of a molecule like water that has a very asymmetric and rotor irregular spectrum, like you see here, the vibration rotation band at 6 microns. So that's how you recognize the molecules, by their patterns. But that pattern is also sensitive to temperature. So here's just an example of carbon monoxide at 200, 500, and 1000 Kelvin. And you see that clearly you can just measure the temperature from the pattern of the lines in a Boltzmann diagram. Okay, so what are we going to do with these data? Well, we're going to look at the inner, very much inner part here of the disks, but that inner part is actually also the result of what happens in the outer part of the disks. Now, we know that ices are always oxygen-rich. CO2 has 2 oxygens, only 1 carbon. Water, of course, has no carbon. So ices in the cold regions where they freeze out are always oxygen-rich, and that means that your gas needs to be carbon-rich, even though overall depleted. But these icy dust grains actually are not stationary, but they move due to the slight friction with the gas. And that means that if you have an icy grain here, say beyond one of the snow lines, so of course water is the most tightly bound, about 150 Kelvin, then comes the CO2 snow line, then the CO snow line. But this icy grain can actually move inward and then enhance carbon and oxygen in the inner disk. So that is one of the signatures that we'll actually be looking for. So here you see sort of a disk structure with the icy pebbles, big icy pebbles in the inner disk, in at least outside the ice line. The gas in the outer disk has a high carbon-over-oxygen ratio, but overall depleted. And this has actually been confirmed by, for several disks by observations with ALMA. And if this is indeed the case and it passes the ice line, then you get high O over H or C over H in the inner disk. But now you put a planet in there, a giant planet that creates a dust trap that locks up the oxygen-rich ices. And then if none of that material can pass through this dust trap, then you actually end up with very low over H or C over H in the inner disk. So what we see is that actually the some of our first results. So this was actually a Titori disk. You see here the very strong silicate feature, the rising continuum. And what you see here also is the CO2 feature that was actually detected already before by Spitzer. And there's a whole heritage here building on the Spitzer results, the pioneering Spitzer results. But what JWST really allows you to do is zoom in and detect many more lines and features than just that one Q branch here of the CO2 that was seen before. And one of the things we noticed very early on, this was the first MIND papers that we had led by Sierra Grant, is actually that this feature over here is not just 12 CO2 a P branch line, but is also 13 CO2. And the detection of 13 CO2 at this level tells us that 12 CO2 is very optically thick and that CO2 is actually much more abundant by about a factor of 100 than we thought previously. So the water, CO2 over water ratio is actually much higher than previously thought. So somehow we're lacking water, and maybe this is consistent with the theory of a cool disk with a cavity where the water is still frozen out, the hot water is taken away. Now, how about other disks? This was one of the next disks for which we obtained data. This is actually a very water-rich disk, just the opposite of GW Look. It's actually completely full of water lines. All of this is real features. None of this is noise. And yes, indeed, we also struggled initially with the wavelength calibration, but that's now all figured out, thanks also to these hundreds of lines that we have from water. So we can actually do fitting of these data. We can fit so-called slab models that are in LTE. The only thing that we fit is the column density and the temperature and the emitting area. And in the case that the emission is optically thin, we actually constrain the product of the column density and the emitting area, basically the number of molecules. And if we do that across sort of the wavelength range, then we see that we actually have both very hot water in the inner disk, in the innermost disk, coming from inside about 0.2 AU. And then we also have somewhat cooler water coming from further out in the disk at about 1 astronomical units. So we're really now probing chemistry on the scales that we are not able to probe with ALMA. With ALMA, we get down to 10 AU. ALMA is completely blind to this part of the disk. And so very interestingly, what we, and this was first pioneered by Banzati et al. For another disk, actually see is that at the ice line, so the coldest water, which is just above the sublimation temperature of water, there actually is an enhancement in the abundance of the cold water. So consistent with this idea of drifting ice grains. Now, there's actually quite a diversity of this chemistry. Here's again our GW loop, and here is the SLAP model fit to it. So really every feature can be fit in here. This is dr tau. Now we put them on the same scales, and now you see indeed that how diverse they are. Some of them have really very bright lines, others have very weak lines with a different chemistry. So here again, zooming in now on the 15 micron region, here we see our CO2-rich disk, which is, see here the Q branch, whereas you have a water-rich disk, you see very clearly these water lines. So we do already see some differentiation in these two disks. Maybe this is a drift-dominated full disk. Also in ALMA, it's very compact, whereas this is actually may have a small cavity in between the water and CO2 snow lines at about 1 astronomical unit. We cannot image that with ALMA yet, but that's something like that would be consistent with this kind of scenario. There's another scenario, and that is that we have no dust trap, no cavity, but we actually have drifting icy grains, but they come in at different times. So the water-rich ice grains will come in first, and then they will actually enhance the water in the inner disk, but then they are basically accreted onto the star. The CO2 ice-rich grains come in a little bit later. They come from a little bit further out in the disk. And so their enhancement is a little bit later. So this is in a paper that's just been submitted. Also very nice work here by Kalian and Ma et al. On the water enhancement, the timed water enhancement in the inner disk. So how about gap disk? How about these transitional disks? Well, there's one prime one, and that is PDS-70, the only disk where we know we have young protoplanets to Jupiter mass planets already in the disk. And you see here this big dust trap, this ice trap. And so you might think, well, maybe there's no water there inside that region where the terrestrial planets are forming. Well, that turns out not to be the case. We actually do see water. Not that much, about 1 North Sea of water is there. So it's not oceans of water, it's about the North Sea of water. But despite the strong dust trap, there is actually some water in the inner region. So we see water in these disks. Many of the Titori disks actually do show quite strong water. That's not at all the case if you go to much lower mass stars. Those of you who were present at Dave Charbonneau's fantastic talk remember that when you go to the late M-type stars, so M5 and later, you have sort of a different type of star. Well, you also have a different type of disk there. This is a very low mass star, an M5, 4.75 star, that you see over here, less than 20% of the solar mass, and its spectrum is completely different from the Titori disks we have seen so far. It's full of hydrocarbons. In fact, in the beginning, we didn't even know what we were looking at. We thought we were looking at a silicate in absorption, but that was not the case. We were looking at enormous bumps of acetylene, 10,000 times more acetylene than we have seen in any other disks. And we also see these other hydrocarbons like diacetylene, but also benzene actually detected in these disks. And this is just to show you that indeed it is about 5 orders of magnitude more acetylene that we have in this disk compared with water than we have in Titori disks. So they're really very different chemically. So what is happening here? Is this really an enhancement of carbon that we're looking at? Or is it a depletion of oxygen? We clearly need to have C over O greater than unity in these disks. But which of the two is it? Are we seeing a destruction of the carbonaceous grains, the hydrocarbon grains, at sort of a soot line or a tar line? Or are we seeing primarily the dust, the water ice being locked up here in a dust trap at only about 1 AU? This is a very low mass stars, changing then the C over O ratio. So this is one possible scenario. An alternative scenario is this timed drifting grains, the hydrocarbons drifting in even later than water and CO2. That's another scenario. But if this is indeed the case, if the carbon-rich grains are destroyed and that gas is subsequently moved, what kind of planets do you actually make? You would make actually carbon-poor planets. And this is actually similar to what may have happened on the early Earth, where basically Jupiter acted as a stop sign, preventing the carbon, preventing the water to drift in, but also carbon grains being destroyed there. So maybe we are seeing some of that over here. Is this source unique? No, it's not. We have another very low mass star that you see over here, published recently in Science, and thanks to the science editor, Keith, who is sitting here in the audience. Beautiful paper. This one is not so rich in C2H2. It's actually a methane. Here is C2H4, C2H6 for the first time in a disk. Here is our acetylene again. Here is our benzene again, CO2, HC3N, diacetylene. I mean, all these molecules are basically waving at us and saying, hey, I'm here. There could be some water hidden in this mess over here, but of lines. There's so many lines contributing here. It's even hard to see the continuum that we have there. And again, we have another paper by Conwar et al. Of yet another very low mass stars that showed the same signature. So even though some of these very low mass stars do show a little bit of water, not certainly all of them are carbon rich. So what we've seen actually is inner disk chemistry is diverse. Main drivers are likely going to be dust evolution and the drift of that and the trapping of that dust. And I'll end here with my conclusions that we have exquisite JWST data, especially with MIRI, large diversity in chemical composition. We don't understand yet everything that is happening, but it's clearly an interplay of dust and this structure. And stay tuned for large samples in the coming year. Thank you.
Thank you. Thank you very much, Ewan, for your talk. So we got time for quick question. Yes, please.
So I'm David Silva from the University of Texas, San Antonio. So Veen, you're a lab astro person. So, given that you're getting these incredible data with all these details, what does that tell you about the work that needs to be done in the lab?
Yeah, that's a very good question. There's a lot of work that needs to be done in the lab on ISIS. I will not talk about that here. But even for these gas phase molecules, you would think that the spectroscopy of acetylene at high temperatures is well known. Well, it's not so much. It's some of the overtones are not that well known, but especially we're now also seeing the 13 C2H2. We're seeing the 13 of all of these molecules. And it turns out the lab spectroscopy is highly incomplete for the 13 isotopologues. It's hard to get anybody to do that spectroscopy. It's not very flashy and it's hard work to do, but it needs to be done because at the moment, I think we're limited by the line list.
Thank you. Thank you to our speaker again. So let's move on. So time is out. So now let's move to the next speaker, which is going to be Iziardo Gregorio Monsalvo, who she will be talking about water at the early stage of the star and planet formation. So can you please reset up the time? Thank you.
Good morning, a pleasure to be here with you. In this talk, following up a bit with what Evin was talking about, I'm going to talk about water, but at the earliest stages of star and planet formation. I'm talking about the protostar phase, because now we know that planets form earlier than we thought, even earlier than in the class 2 stage. Okay, so why water? Water is a key molecule in the universe. It is an essential molecule for sustaining life, as we know. It is a primary coolant in the regions where stars and planets form. And also there is something very interesting about water snowline and its key in planet formation and in their chemical composition, right? And water is also relevant to understand the origin of the oceans on Earth, and also our own origins. Nevertheless, observations of water is really a difficult task from Earth, right? Because we have atmosphere and we have plenty of water in our atmosphere. So we have two possibilities there. The first one is to observe with space telescopes, right? You can see that in the plot, the transmission of the atmosphere. So, or we go into space, like we do with Herschel and James Webb, and we try to observe water in the infrared, or we go to a very high place and dry place, like, for example, the Atacama Desert, and we observe with the facilities we have there, like the Atacama Large Millimeter Array, ALMA, or APEX single dish antennas, right? Okay, so in relation to space telescopes, we have been doing some progresses with Herschel and with James Webb. I would like to highlight a couple of works there that have been already shown in her presentation. The first one is Herschel Large Program, WISH program, which stands for Water in Star-Forming Regions with Herschel. And well, there we make some progresses into understanding the cold component of water into protostars. Very recently, the James Webb is providing these very nice results on detection of water in the inner part of disk with large gaps like PDS 70, where we know that planet formation is at work. ALMA is also providing some nice results, okay, after many, many hours of integration time. So I have picked up two recent publications that have been press releases at TISO. The first one is related to the ratio between deuterating and the main isotope of water in a disk surrounding a protostar that is undergoing an outburst, okay? And they found that this ratio is comparable to protostellar envelopes and comets. So this is telling us something about the origin of water in protoplanetary disk. The second one is a very recent press release where the authors detected water vapor in the famous HL tau disk. They detected 3 transitions in the main isotopes, and the 3 transitions are inside the water snow line. And in particular, the one the one there at 321 gigahertz is located just at the very center of the disk, okay, inside the first gap where within planet formation is happening. Okay, but these results that I show with ALMA needs plenty of integration time, okay, many hours of integration time for very fine detections. There is another way to study water while we wait for the very future capabilities, and it's through the water maser emission. What's a maser? Maser stands for microwave amplification of stimulated emission of radiation. It's like having a laser in the space without the resonant cavity, of course, and they occur naturally in space for some molecules and for some specific transitions. We know that the pumping mechanism for masers require high density and high temperature regions, and they can be excited through collisional or radiative effects. So the beauty of masers, of water masers in particular, is that they show a very compact emission, very intense, and very narrow spectral lines. So they are perfect for studying them with interferometers. So they are a powerful tool for studying the local physical conditions, the circular stellar structure, and the dynamics at subarcecond spatial scales. In the past, we did plenty of studies using the water maser molecule at 22 gigahertz, basically because the previous facilities were operating in centimeter wavelengths, right? So now we know that water masers, at least at 22 gigahertz, emit in a wide range of masses from low mass to high mass protostars, and that they are good tracer of both mass loss activity and disk-like structures, right? I have selected here this example of observations in time, okay, of the evolution of a wide angle outflow traced by masers. And in the right-hand side, you can see here how the water masers are distributed perpendicular to the jet emission in intermediate mass protostar. Okay, but we are lucky, and water masers emit plenty of maser transitions in the sub-millimeter regime. Here you can see how many transitions fall inside the ALMA bands. So we have at least one transition in every single ALMA band. And these make APEX and ALMA excellent facilities to study water masers in the submillimeter regime. Nevertheless, if you have a look into the literature, there are very few studies using submillimeter water masers to characterize water in protostars, right? And most of them are done in the transitions 321 and 325 gigahertz, which have been proven to trace jet these structures in these high-mass giant stellar objects. These are a couple of examples of these existing works, right? The first one is a study using water maser at 22 gigahertz and 321 gigahertz in Cepheus A. So here the authors showed that masers at 22 gigahertz are tracing a perpendicular structure to the jet that is well traced by the masers at 321 gigahertz. So we have two different transitions tracing two different phenomena in this high-mass protostar. The other one is Orion Source 1, okay? This is a totally different case. This time, the authors represented here the masers at 22 gigahertz and at 325 gigahertz. They are tracing, both are tracing a jet-like structure, but the masers in the submillimeter regime are tracing the inner part of the jet, okay? So maybe we are seeing some kind of layers of the jet because of the different conditions there. So the interesting thing is that since different water masers transitions can be pumped over a range of conditions, we need the observation of different lines to constrain the physical conditions in the masing region, which is associated to these like structures, right? So here I have, just for illustrating, I have included the different transitions for pumping these three transitions I've been talking about. Okay, so inspired by this, we started a search for water masers in 321 and 325 gigahertz in 20,000 sources, which are prominent emitters at 22 gigahertz and spanning a wide range of luminosity from low mass to high mass. And we did this survey with APEX antenna. It's very difficult to go with a blind survey to ALMA directly, so we had to start with a single disk. And since it's a very intense emission, we thought we would detect something there, right? And that was the case. These are the detections. We had 6 detections, okay? Most of them emit at both frequencies. And this is like 30% of the detection rate, right? Something we saw is that the luminosity of the maser correlates well with the luminosity, volumetric luminosity of the central giant stellar object, as was proven before with the 22 gigahertz transition. And another interesting thing is that there was no maser emission below a certain luminosity. In this case, below 750 solar luminosities, right? Okay, so next step was to have a look into the ALMA archive, but we have very few cases of sources observed in these transitions because of the atmosphere there. So people run away from this wave range, right, because of the low transmission. Only one source was previously observed with ALMA. Actually, it has been published a couple of years ago. It's about, the source is 255, which we included in our survey. In this case, the author wanted to prove the relation between accretion bursts and water maser variability. Something I forgot to comment is that these masers are very variable, right? But we do not have properly characterized the variability of the masers as a function of the mass. So maybe that has something to do with the non-detection of the masers in the low mass regime also, right? In this case, the author did not conclude anything about variability, but what they conclude is that the masers at this frequency in this high mass protostar are tracing two different things. The most obvious thing is the jet-like structure, but they claim that they also saw some kind of rotation feature at the center, which could be associated to rotating this envelope, right? And this is very interesting because we are talking about high mass protostars and these structures impacting the formation mechanism of these high mass young stellar objects. So we have just applied to ALMA to follow up our single disk study, and fortunately we have we got approved a cycle 11 proposal to resolve the morphology and the kinematic of our detection. So hopefully in the next time I talk about this, I will be able to show these high angular resolution observations. But what about low mass, in the low mass regime? Okay, you remember in our survey, we didn't detect any emission in the 2 millimeter in the low mass regime, right? But actually there is one source that has been observed with ALMA. It's L1448. It is a class 0 protostar, and it has a very nice molecular outflow that also emits in SIO. You can see it here, okay? This is tracing shocks. And there we saw emission in the 325 gigahertz transition. So maybe we didn't detect it because of the sensitivity or because of the variability of these masers. And the distribution of this 325 gigahertz transition was very near the central protostar in these two places, following the same kinematics of the molecular outflow. So we think it is tracing the outflowing material. And a nice surprise is that we detect also this transition at 183 gigahertz, quite intense. And when we represent the emission in colors, okay, the velocity is following the outflowing material, and it's just at the regions where the SIO seems to be interacting with the rest of the material of the cloud. So theoretically, it was predicted that this transition was pumped, what was excited through shocks. And I think this is what we are seeing here if we compare with SIO distribution, right? So we are trying to follow up these studies also. We have approved a single disk survey at Apex, and we have just received the data. So this is very promising. So to conclude and to talk about a bit about the open questions, water masers are powerful to study star and planet formation processes at the very earliest stages of star and planet formation. ALMA offers a very good chance to do these studies at sub-R-second resolution. There is a lot of work to do. It's a very unexplored topic, and there are plenty of open questions. I have included here a few of them. For example, what is the relation of the maser emission with the outflows properties, with the protostar luminosity? Is there any relation between accretion, episodic accretion, and ejection processes, outbursts, with the variability of the masers? What is the relation with the chemistry of the region, with the shock tracers, right? And also with the states of the evolution of young stellar objects. So we need larger surveys, monitoring campaigns, of course, and ALMA follow-up studies to understand this. Okay, thank you very much.
Okay, so do we have time for quick question in the room? I'm also checking online if there's anybody watching a question on the chat. So yes.
Hi. Quick question about the outbursts, the relation of masers to outbursts. I mean, how would we trace? That's new to me. I mean, how do we trace outbursts of maser? I can see jets, and then maybe the knots have maser emission. I don't know, but the outburst. How can we study outbursts using masers, water masers?
What we can do is, once we know there is an outburst, which is to me the tricky thing, right? There are different ways to do that, but okay. Once we know a source is outbursting, to go and monitor the presence, the flux density, and the presence of different maser components in a specific transition, right? Because the idea is that if you have an outburst, you will have an enhancement of the water masers, high density, higher temperature, right? So, and hopefully in different transitions, because different transitions are affected by different temperature and density conditions. But we need, this quick reaction.
Okay, great. So let's thank again our speaker. So let's move on. Our next speaker going to be Antonio Garoffi, who will be talking about hunting protoplanets, the planet formation seen by ground-based telescopes.
What do I press here to move on? Yes, okay, good. Hi, everybody. So actually, most of you don't know me, I believe. I'm Antonio Garuffi. I'm also in the field of planet formation. And since we have a very slightly diverse background, I think, in the audience, I thought to give you a little bit of background of where we stand in our search for protoplanets. So really the very moment when actually a planet is forming in order to understand the planet formation. And I'd like to start with a few premises that I think it's important to keep in mind, even though they're probably kind of obvious. So we know that planet formation is efficient, right? We also know that this occurs quickly. This is just because we need to make these planets in the disk, and the disk is typically gone after 2 or 3 mega years. So at least giant planets must be formed very early. Yet we have a number of theoretical barriers toward the formation of planets that we don't quite understand. At least observationally, we're trying to understand how to overcome this barrier, with the most important one being the so-called meter barrier toward the formation of larger bodies at the meter stage. And we have now an increasing evidence that planets are already formed in the typical planet-forming disk or protoplanetary disk that you see. That's why actually we switch typically the name from protoplanetary disk to planet-forming disk. We believe this is more appropriate as a name, because probably planets are already formed or are really in the act of forming. So in order to see directly the planet formation, the best way, especially if you want to see the protoplanets, the best way, probably the only way to see a protoplanet is to read the direct imaging. However, unlike direct imaging for planets, we have the limit that we need to go a little bit farther away, right? We cannot really look at protoplanets at 15 parsecs just because we haven't any subforming region that is so close. So we need to go to the Taurus subforming region, to the Lupus subforming region, or the Chameleon, and so on. And this is typically at least 150 parsecs away from us. So for direct imaging, this clearly means that we have 1 order of magnitude worse resolution. And this talk I basically have 2 mini parts. The first one is the indirect characterization of the planet formation through planet-forming disk, and this is pretty successful, as you can see in the title. While the second one would be on protoplanet itself, and this, to some extent, also successful, but for sure less. So the big revolution over the last decade has been really from the ground, thanks to 8-meter telescopes, in particular, all equipped with extreme adaptive optics, so the new generation of adaptive optics that can really correct efficiently the aberration from the atmosphere, and in particular implementing some pipelines and some post-processing reduction that we call differential imaging, in order to basically get rid of the PSF, of the stellar flux, because we need to actually see something in the near infrared, where actually the near infrared photon from the star is dominating, right? And as you can see here, the first images are from the late 90s or beginning of the century. So you can clearly see that now in these 20 and 10 years in particular, we really improved a lot the quality of the image that we can obtain for this disk. We did it with a number of differential imaging. Here you see the list of most used differential imaging. I don't want to go into the detail. I just want to point to the fact that this polarimetric differential imaging has been extremely useful for characterizing planet-forming disks from the ground, basically exploiting the fact that the stellar light is unpolarized, let's say mainly unpolarized, whereas the scattered light from the disk is to a large extent polarized, right? So with some math, we can basically get rid of the unpolarized light and be left with the polarized light from the scattered light from the disk. And whereas you can see from the symbol here, if you want to see the protoplanet or a planet, then you need to use other techniques like the angular differential imaging. James Webb is doing something different by staying on the same line, and reference side differential imaging, which is also useful from space, of course. So the big revolution has really been to characterize what we call here intermediate disks. So back in the days of HST, we could only basically access this very large disk here, larger than 100 AU, so much larger than the solar system typically. And we basically had no access to this inner part of the disk where we believe most planets actually form. As you can see here with ground-based telescope, now we have access to this disk here, and automatically we basically switch to a few tens or even only 10 disks being imaged at the time of HST, at the first time of HST, to hundreds. Now we have 300 disks observed from the ground with or basically our technique. And here you can see basically the figure that we put in the Protostar and Planets chapter led by Miriam Benisti, where we summarize our achievement. And clearly, the small disks are still a little bit out of reach for now for us, and this is where the Extremely Large Telescope in the next decade will really bring us and then actually characterize the disks that are really similar probably to what has formed the planet, the solar system, or even smaller systems. Okay, if we had to summarize, we were to summarize in one sentence, what is the main result on planet-forming disks for the planet formation, is really that most disks do show substructures. So if they are large and extended enough, if they are bright enough, we typically see substructure. And this is just a survey that we have done from the ground when I started my PhD, actually 12 years ago. We could really see the variety of structure in these disks. So typically spirals, large cavities, rings, gaps that you also typically see with ALMA, of course, now. And actually, ALMA came online after this survey, and of course, somehow confirmed the variety of substructure. And then you see the very famous image of HL tau, which I remind you is from a very embedded and early object, right? This is, you can see here in the original paper, the envelope, the natal envelope from which the star and the disk are formed are still there. So somehow this has been interpreted as a signpost of planet formation occurring very early. We don't know yet whether this is true because we don't know whether substructure are actually due to protoplanets in the disk, but this is certainly one of the explanations that we have. And now, well, now we have the variety of disks here observed from the ground. You can see in the chapter by Miriam Benisti, the Protostar and Planet chapter, and from ALMA, as you can see in Sean Andrews at the view here. So we know the majority of disks do show substructure. To some extent, some of these will be due to protoplanets, right? Not all of them, probably. There are many theoretical works that try to address which one of these can actually be due to protoplanets, which one not, and so on. But we believe at least some of these are due to protoplanets embedded in this disk. So somehow we need to find it. This is just one of the pieces of evidence that we have to actually understand why we think the planets are already there, and that is very good to display this. Here you can see basically the average mass of disk at different stages, and the typical disk that you see in these images are class 2, some maybe are class 1, but most of these are class 2. And you can see the mass of this disk is actually lower than the average mass of the exoplanet system that we have. So we need to have already formed planets in this disk. There are a number of caveats. These are not isolated box. We know that there are replenishments and so on. But let's take it as it is for now, and we believe that planets should be already there. So let's search for these protoplanets. And as you can see already, I say unsuccessful because probably we would think to have obtained more protoplanets at this stage. Luckily, we have obtained one, as you know, PDF70 has been shown by Vina already and many other speakers. Here is PDF70b, and then later on we found PDF70c. This is from VLT sphere, so basically we are seeing the thermal emission from this protoplanet, strong thermal emission because it's, the planet is still contracting probably. And you can see the large cavity from the disk, so basically this also favor the detection of these protoplanets, right? Because we have no contribution from the disk in this location here. This is something very important to keep in mind when we search for protoplanets. So this is basically the plethora of different observations on this object here. PDF70bc has been detected with the H-alpha, so basically signpost of accretion probably onto this planet here. And without going too much into the detail, I want to underline the importance of the synergetic employment of different techniques, right? Because we have thermal emission from sphere, accretion in this case from MUSE, circumplanetary dust detected by ALMA, just, probably the disk from which moons may actually form. But the important thing is that really all these different tracers confirm the detection of these protoplanets. That's why we are so sure that this actually detection of protoplanets, and that's a very important point. In fact, as of today, PDF70, I think we kind of all agree that it's the only system with confirmed protoplanets. We have some candidates, and I'll show in the next slide, but this is certainly the most robust detection of a protoplanet today. So in general, the paucity of protoplanets is the main conundrum of the field, I believe, and this is where we need to work more in order to find these protoplanets, or at least understand why we haven't detected many more. And Well, as I said, we have a number of other candidates without really going into detail, and just pick up two on behalf of all the others that we have. But in general, I think that as a community, we are still missing somehow a protocol to define what is actually a protoplanet detection, right? Here I'm just listing a number of possible criteria that we may want, not necessarily, we may want to actually put in the protocol to define the detection of a protoplanet. Detection of orbital motion, do we want it? Yes, maybe, but possibly the disk is also rotating, I guess. Spatial separation from the disk, do we want it? Well, not necessarily, right? In the end, we want to see these protoplanets embedded in the disk. So of course, this is facilitating the detection, but this is not necessarily something that we want. Accretion signature, yes, of course, this is ideal because, if a HAL5 emission from a point source and you're not sure about this is, of course, a stronger supporting proof that this is the planet. But again, I'm not sure that all the protoplanets will be accreting. Maybe some of them, for whatever reason, the accretion is halted. Circumplanetary dust, also ideal, but not necessarily. Detectable photosphere, of course, this is ideal, but we know that we have a lot of dust, like in this example here. This is only detecting in dust because it's polarized light, so it's scattered light, for example. So it means, in general, I think it's not always easy. Actually, it would be very hard to detect the photosphere. So I think as a community, in the end, we will have to sit together and define a protocol to determine the detection of a protoplanet. Okay, I just want to put this. I think it's really highlighting well what is the difficulty of detecting a protoplanet. This is a simulation by Yuri Zhiragi. I don't know actually the detail of the simulation, but I think it's really, really clear what is the difficulty of detecting a tiny protoplanet or even a circumplanetary disk when you have the prominent circumstellar disk around it, right? The elephant in the room is really the disk, and this is yielding a lot of contrast. So the contrast between the disk itself, not only the star, we have a star, of course, it's the first problem, and then we have a contrast with the disk, but we also have extinction exerting by the disk onto the planetary flux, and then we have confusion because we don't know whether a point source is actually disk features or a protoplanet itself. So this is clearly highlighting the difficulty. And so in the final slide, I'm actually trying to put together what are the possible explanations for the non-detection of protoplanets from my point of view. And the first one is that all the planets are basically smaller. So they are colder. So maybe, the black body emission peaks at different wavelengths from where we search for now. Like, for example, with SPHERE, we search at 2 microns. So it's possible that, it's just colder. The second, I think, is very important personally, they are heavily extincted. So, most of the 2 micron flux that we search for in SPHERE is actually extincted by the disk. And the third one, they are all closer in. So, all the hot Jupiters that we have from Kepler, somehow they form maybe even farther away, but then they already migrated inward. The fourth one, hard to explain, have not formed yet, then I don't know what to search for, but let's say I put it here still to be comprehensive. And so finally, what do we have to do? Well, it depends what explanation, right? So James Webb would be very good if this is a problem of small or extended planets, because we can go to longer wavelengths. Similarly, we can do it now from the ground with VLT-ERIS that I have an open time program approved. If they're closer in, then we need to wait for the extreme telescopes in order to see maybe, these very close in planets close to the star. So I conclude here. Thank you very much.
So we got time for questions from the room or either from online. Yes.
Hello, I have a question about the gas because I miss a bit of comment on how the presence of a planet affects the gas emission, where you can see actually, even if you don't detect the planet, how the gas kinematics is affected. So maybe this is also a good combination to double check if there is a presence of planets forming there.
Yes, yes. I believe you're talking about what we call kinks, in the field. So basically, when we observe, the orbital motion of the gas in this planet-forming disk, sometimes we see deviation from the typical Keplerian motion that we expect. And people are also searching for this signature in order to indirectly claim a detection of a planet. Personally, I think we will need at least one confirmation, direct detection of a planet and connecting with maybe a kink. Until then, this is a very useful indirect probe of planets, but in the end, we need a photo. This is my point of view, right? And then the other thing that I'm learning from people working on this is that if you look carefully, then you see a lot of these kinks in disks. So we really need to understand what are all the possible perturbations to the capillary motion of gas in the disk.
Any other questions? Yes.
I see you listed a program on the VLT with Iris.
Yeah.
PETs. Can you say more about it?
Not yet, unfortunately. Data still coming. We have some issue with the data reduction. We are improving, but we only obtain like 1/4 of the observation, so it will come soon.
Yeah, one more here.
Quick question. Will be observed PDSC 70 in future?
How will we observe PDS-70C? Sorry?
Yes, because we said we didn't, maybe it's not the planets in this disk. Yes, it's in future we maybe more find observatory data and maybe.
Okay, so you think it's a disk feature, not a planet? You're saying that, sorry, I misunderstood maybe.
I mean, we talk about PDC 70 and
Yeah.
said it maybe not a planet.
Oh, yeah.
Maybe in the future we have a lot of data and.
Yeah, sure. I mean, then the difficulty for that object is it's very close to the disk, right? So in that case, the confusion is really the main problem. That's why initially the sphere people probably did not really claim that detection because it was too close to the disk. Then what is convincing is the H-alpha detection, I believe. Then you need to have something really special there, either accretion or even a flowing, whatever. But then, you know, H-alpha could also be somehow indirectly disk feature, but at the moment, I think it's pretty robust detection. Maybe
Okay, great. It thanks our speaker
Thank you.
again. So moving to our last speaker in the session, who's going to be Anastasia Topsheva, who she will be talking about ices on bubble in protoplanetary disk.
Okay. Hello. Yes. This, okay, and this come back, and this slide. Okay. Dear colleagues, I'm pleased to give a talk on the symposium. Thank you for this opportunity. My talk will be about ices on pebbles in protoplanetary disk. We did this work with my colleagues, which you can see on the slide here. And protoplanetary disk, the planet form, does grows to the size of centimeters there, and we caught grains with size approximately from 1 millimeter to 1 centimeter pebbles. And planetesimals can form pebbles as a result of streaming instability, and pebbles also important in this scenario called pebble accretion, and the chemical composition of pebbles affect the atmospheric composition of forming planet. That is why it is important to study. We run numerical simulation using the Fiasat code for the protoplanetary disk evolution and dynamic. This code developed by Vorobyov et al. 2018 and modified by Malirova et al. 2021. It code include consistent thermal balance calculated, dynamic and phase transition of volatiles. This hydrodynamic code using the sync disk approximation, and it includes disk self-gravity, turbulent viscosity, thermal balance, and dust evolution, and dust drift relative to the gas is very important, and also including in our model. We have 3 main equations. The first is mass compression, the second Navier-Stokes, and the third is thermal energy. We consider 4 volatile molecules which can be present on the gas, small dust, grow dust, including pebble. The initial condition, all molecules in the ice on small grains. And after the evolution, they can change their phase station. While the 4 molecules, because they observed in protostellar core and also have a higher abundance, which is described in paper Oberg et al. 2011. And if the grains has the ice mantle, the growth have a higher fragmentation velocity, 5 meters per second. If dust hasn't the ice mantle, the grains have low fragmentation velocity, 0.5 meter per second. And we consider two models with different initial clouds masses. The first is low massive model and the second more massive model, but we focus on the first and the second we use only look how influence in the more massive disk on our results. The both systems are gravitation unstable. The total mass relative to the mass of the stars, and we have in this model two dust population, small dust and grow dust. Stokes number is used to describe dust dynamic, and it depends on the dust size and gas parameter, density and South speed. We consider large grains with higher Stokes number and large radius to be payable, and we consider threshold value Stokes number 0.01 and grain size 0.05 centimeter, and vary them to see how it's influenced in our parameters. And we use the definition on pebbles from paper Vorobyov et al. 2023, but we modified it because we don't lose pebbles some region. Okay, I skip this slide. And this is our result. Is evolution of a disk parameter. The x-axis show time, the y-axis show distance from the stars. The panels shows the surface density of gas, surface density of dust growth, surface density small dust, maximum dust size, dust to gas mass ratio, surface density of pebbles, and a maximum dust size relative to the fragmentation barriers, Stokes number, and minimum dust size of pebbles. As we can see, the pebbles form early disk formation, 50,000 years, and blue line shows the water snow line, and where pebble exists beyond the snow line. And this is a result radial distribution of molecules on pebbles. And we have 4 molecules, and we see a lot of abundance ices on pebbles, H2O, CO2. H2O ice have a lot of abundance in inner and outer disk, and CO2 only inner. But if you look for CH4 and CO, we see low abundance this ice on pebbles because CH4 and CO ice snow line form later, and it's because this we see there. This slide shows the radial distribution of solid components in the protoplanetary disk for 3 times, 2, 3, and 500,000 years. Upper panel show refractory relative to the gas. We see a lot of dust inner disk because radial drift, and the middle panel we see then the amount of pebbles and grow dust, and we see also accumulated ice near the snow line, for example, and here is CO. And if you look the low panel, we see ice on fraction on pebbles, and we see a lot of H2O, CO2 on pebbles, and CH4 and CO we see in outer disk. It is interesting. And this slide shows the total mass disk integrated over the entire disk for all components and gas, small dust, ground dust, and pebbles, the black line. And we see this model both look like the similar, but the different only everything happen in the more massive later. And we, if we estimated total mass of pebbles is near with 150 Earth mass, which is considered with minimum mass solar nebula. And this slide shows the chemical composition of gas and ice, we see a lot of molecules in gas, and the upper panel for low massive model, the low panel for more massive model for 3 times. And also we look on the pebbles, we see a lot of H2O, CO2 on pebbles, and if we assume the pebbles are created the future forming planet, atmospheric, they have a lot of oxygen and then carbon. It is interesting conclusion, but need to remember that we have only 4 molecules and we have only absorption and desorption, chemical reaction. And maybe we put more molecules and changed our results, but now it is like that. And the last slide show the definition of pebbles. We want to look how influence these parameters if we changed, for example, APEP 0 and STOX 0. And we see APEP 0 no changed our results, maybe talk a little bit, but if we look for the STOX 0, it's changed our results more. And STOX 0 burial from 0.01 to 0.05, and we doesn't have grains with STOX more 0.01. And my conclusion, we showed that pebbles are presented in the protoplanet disk early 50,000 years after the disk formation. The maximum total mass of pebbles correlated with minimum mass solar nebula, and we have a lot of H2O, CO2 on pebbles. Maybe in the future planet have a lot of oxygen, more carbons, and most of pebbles in the model have STOX from 0.01 to 0.05, and which should be taken into account in model of planet formation. Thank you for the attention, and I know we have a time for questions.
Thank you very much for your talk. So we have time for questions. Yes. Can you just use that mic there? Yeah.
Hi, Anastasia. Thank you for this presentation. I want to know generally, how can your studies on the chemical composition of the icy mountains or pebbles help us understand the CTO ratio in the gas after these pebbles drift and evaporate in the disk?
You mean about, sorry, I come back. No, it is not. You mean how
So you know the pebble, when they drift, they might cross the snow line, and so they can heat up and evaporate and start to evaporate, releasing the volatiles into the gas in the disk. And so the CTO ratio, or this lead to higher concentration of oxygen in the carbon and the disk in the gas after.
Yes.
In the gas path. So to constrain the CTO ratio in the gas after these pebbles evaporate or drift, so it's complex because it depends on the atmospheric composition, or on the composition of the pebbles and the details of the process of their evaporation. So your models, how can they help us to understand or constrain the CTO ratio after the
I think it's a talk, I don't know how to say. This this one. Yes. This is gas composition. Yes, we have H2O, CO2. I don't understand. Maybe you help me.
So if you want
Okay.
any comments, yeah, you can go on.
Yes, because it's my colleague.
So basically, I'm the co-author of this work. Basically, this is also already accounted in this work. So this gas composition is a result of pebble drift already. So what you see in these pictures, the composition of the gas, the first column of each slide panel.
Thank you. Sorry.
Thank you. So any
I don't
more
understand.
comments or questions before closing? Let me check if there is anybody online. No. So let's thank our speaker again.
Thank you.
So thanks to all the speakers for the session. And now it's time for lunch. Enjoy your lunch. And just one quick announcement. So there is going to be a movie screening in the Ballroom West about the Star Chasers of Senegal that Maram has played yesterday. If you're interested in watching it, just go there and enjoy it. So see you on the next session at 1:30. It starts in 10 minutes.
got a problem with that because I almost did that same thing.
Right. In the meantime, you guys not give me the person, but it's like 5 minutes.
And he was running things on some of the first desktops that were out. Yeah. And he had an entire room full of them because he could only get them to.
When I was his postdoc, he had gotten a new data channel 4.
Okay.
Which, as you recall, they were referred to as the trade for each other.
Okay.
This was one that almost worked. The floating point unit had some bugs in it.
Okay, that would be an interesting problem for him.
It could not add 2 plus 2.
Okay.
It would give you like 3.97 or something like
Okay,
that.
so it got close.
It got close. Processor while they waited to update.
I had we
Yeah, the green thing is for pointing. And
Yeah.
this is for passing slides
Yes,
or
okay.
coming back. But you will be pointing with this and passing with that, right?
Sure, yeah, of
Okay,
course,
everybody's doing that.
everybody's doing that.
Okay, we are ready to go then. Welcome to this session. I'm going to chair this second session of the year. I am Itziar de Gregorio from ISO. And we are going to start with Binjan. And I would like also to welcome to the people online. Okay, Bin?
Okay. Thank you. I want to first thank organizer to offer this great opportunity for me to share with you some recent work on the group of extraordinary objects known as distant comets. Have to point out some of this work have been done our brilliant colleagues sitting in this room today. So for ordinary comets, the activity, meaning showing coma and tail, usually starts when they're within 5 AU. That is because for comets, the primary component is water ice. Volatile component is water ice, which sublimates at equilibrium temperature of 150 Kelvin. That it's corresponding to the orbit of Jupiter at 5 AU. So that's not surprising. Most active comets are detected within the orbit of Jupiter. However, in recent years, some comets are detected far beyond Jupiter. So first object in this category is C2017K2. It was discovered by the Pan-STARRS Survey Telescope in Hawaii. It showed activity at 16 AU upon discovery, and follow-up observations using HSD show that this object, its activity began up to 35 AU. At that time, this is unprecedented distance. There's no other object been active at such a large distance. And then soon after, there's another object called C2014 UN271. And this object was discovered by this dark energy survey. And this object was active at almost 30 AU from the sun. And the discovery was announced in 2021. And upon announcement, and this object quickly became a hot target. And there's a French group, they got ALMA time, and they detected the thermal emission from this object when it was 20 AU from the sun. And they derived effective diameter of this object to be about 140 kilometers. And later, Hui and Jewett et al., they observed this object use HSD, and they derived a slightly smaller diameter. It's about 120 kilometers across. So for people in this room study planets and asteroids, 100-kilometer sized object, it's nothing. It's tiny. But for people study comets, this is really a big deal. Here I show you that the measured nuclear size of various comets. As you can see, most comets, they're only a few kilometers across. And in comparison, this comet UN271 is 50 times bigger than a typical comet. So it's gigantic. It turns out, besides its large size, the activity of this object is also interesting. So Kelly et al., they studied broadband photometry of this comet from when it was at 19 to 20 AU from July 2021 to February 2022. And they found this comet experienced a 3-hour burst during the observed period. And the modeled outbursts are showing in purple here. Besides outburst, the morphology of this object also changed. In the beginning, it shows one overall spherical profile, but as time progresses, the object started to elongate it along to the east. So unfortunately, at the time, JWST was not available, and we didn't observe any gas. So at the present, we actually don't know what is the cost of this outburst. Could be due to sublimation of CO or CO2, but since we have no direct observation, so we don't really know. Okay, so Comet K2 and UN271 are celebrities among comets, but there are other comets. They're less known, but they're just equally interesting, if not more. So the third object in this category is called C2010U3. It was first discovered in the Mountain Lemon 1.5 meter telescope image. And at the time, the comet appeared active at a distance of 18 AU from the sun. And Hui et al., they used a search tool and they found a pre-discovery image in the CFHT archive. And they found image back to 2005, that's 5 years pre-discovery, and they pushed the record of activity to almost 26 AU. Okay, then if we compare U3 with K2, you already see these two objects are drastically different. K2 is dominated by large millimeter-sized grains. So it showed this spherical coma, whereas U3 is dominated by micron-sized small particles. So it shows this thin tail. And besides their morphology, the activity is also different. K2 showed a steady activity. It just gradually becomes brighter as it's approaching the sun. But for U3, it actually showed outbursts beyond 20 AU. It's kind of like a UN 271. Okay, so the last object in this category is C2019 E3. This is just the membership of this object as an ultra-distant comet just came out this year by Hui et al. 2024. They use this nice tool called the Solar System Image Search Tool, and they searched for pre-discovery images of the E3, and they found images again back 5 years before the discovery, and using various telescopes, DECAM and PanSTARRS and VST, and so they found this object was active beyond 23 AU. Okay, so I want to point out that the morphology of E3 is kind of similar to K2. It's also this spherical that indicates similarly, E2's coma is also dominated by millimeter-sized large grains. And also that E3 shows a steady development of a mass loss rate, again, similar to K2. So it turns out E3 is also one of our JWST targets. I will talk about this in a moment. Okay, so I want to take a moment to highlight why we care about these distant comets, why they're important. The reasons are threefold. These objects are, several of these objects are believed to be dynamically new. That means they have been staying most of the time in the Oort clouds, that at the edge of our solar system, and they are likely experienced minimal amount of solar heating and alteration. Therefore, they offered a great opportunity for us to study well-preserved planetesimals from the early solar system. Most importantly, these objects are very bright and active at a large distance from the sun. As they're moving towards the inner solar system, they offer us this unprecedented opportunity to monitor their activity over a large range of heliocentric distance. Okay, so for this object, what makes them unique is their activity. So what is driving their activity? Here I listed some commonly proposed mechanisms can drive activity. It could be due to the water ice transition. I will talk more about this. Could be since they're in the Oort cloud and their surface has been bombarded by cosmic rays, and then their unstable radicals could form on their surface, or impact could also generate observable dust plume. And as recently observed on the surface of 67P, the Rosetta target, that surface landslides and avalanches can also create distant activity. But we think the most likely driving force of this distant activity is due to sublimation of supervolatiles. For example, the CO and CO2. Unfortunately, we couldn't observe CO2 from ground, but we can search for CO in the radio using ground-based telescope. So that's, we used JCMT in Hawaii. After 2 years, we finally detected a CO2-1 transition, shown here. That's when the comet was 6.7 AU from the sun. So our detection of the CO line supports our hypothesis. The distant activity of these comets are due to sublimation of supervolatiles. Okay, so for other comets, the expected trend is that the comet is getting closer to the sun and the CO emission gets stronger, as demonstrated here by the observation of Hale-Bopp, showing in green and blue dots here. But it turns out it's not the case for K2. We monitored the K2 as it's approaching its perihelion first using JCMT. And soon after the first discovery, we noticed just a few months after the discovery, the detected CO emission line is 10 times weaker than our model prediction. And as the comet moved to the southern hemisphere, we switched to the apex in Chile. And then we didn't get a beautiful spectrum. Unfortunately, even at the perihelion, CO was hardly detected. And we follow it up post-perihelion, 8 months after, so the CO line it's kind of there, but it's very weak. But fortunately, the HCN line is very strong. So we managed to monitor the activity using the HCN line. Okay, besides volatiles, what interested me most of this object is the offered opportunity to tackle this water ice problem in comets. So, to give you a little bit background, water ice structure is sensitive to temperature. When formed under cold temperature, say below 50 Kelvin, water molecules doesn't have enough energy to order themselves, so they condense out into this loosely structured amorphous phase. And this amorphous water ice is unstable. As it warms up, it transits to crystalline phase. These water molecules can arrange themselves in a more orderly manner. And then their morphology changes. There's more porous. The amorphous ice is more porous, so they can trap supervolatiles in their holes. And as they transit to crystalline phase, then these trapped supervolatiles can be released. And for decades, this water ice transition from amorphous phase to crystalline phase has been proposed to trigger outbursts and distant activities in comets. Okay, so it turns out to understand the water ice structure is very important for our understanding of the solar system formation. Here I show two proposed scenarios of solar system formation. So the solar disk could form hot. That means near the sun, the disk can be heated above 300 Kelvin. And as time progresses, the disk cools down and volatiles gradually condense out to form solids in the solar nebula. Whereas in the cold formation scenario, that is the solar nebula never been heated above 80 Kelvin. So all the ice is inherited from ISM, nothing gets heated up before. So if we study these water ice structures in the solar system, then if they are mostly crystalline, that supports the solar system formed hot. But if their objects are mostly made of amorphous ice, that would support the cold formation scenario. Okay, so how do we do it? How do we study the ice structure? So due to this stretching and bending modes, as we see this morning, that water ice shows a very strong feature in the infrared. This 1.5 and 2 micron. Specifically, crystalline ice, especially cold crystalline ice, shows a very sharp feature here at 1.65 micron. So we can observe these comets in the near-infrared to set constraint on their water content. But it turns out it's very difficult. First of all, it's very difficult to detect water ice in the comet spectrum remotely. For decades, we only have detection in handful of comets. And except for one outbursting comet, that 1.5 micron feature have never been observed in the comet spectrum. So we really don't know what the comets are made of. So here is JWST came into play. It turns out that crystalline ice shows another very strong feature in the 3 micron region here. So point out by these 2 arrows, that's the sharp peak feature, and this can see better here. The green line is the crystalline ice. You can see this sharp feature is known as Fresnel peak. And then if you see this feature, then you know this ice is in crystalline phase. But it's very difficult to observe this thing from ground because atmosphere is so opaque. Then to do this, we have to go to space. So that's the goal of our JWST proposal is to study distant comet and try to understand their water ice content, because this object we choose, their perihelion is beyond 9 AU, so they never gets close to the sun. So we think their water ice is pristine. Okay, so before I show you some results, I have to point out, as Sarah showed yesterday, that IFU mode of NIRSPEC is tiny. It's only 3 micron, 3 arc seconds. And to observe moving target is quite challenging. If the object orbit is not well determined, the object could be out of field or near the edge. So before we took observation, we tried hard to improve the astrometry of our target's orbit. So when I see this, it's what a big relief. Actually, our target is right at the center. Okay, I'll show you our detection. So very nice. We detected water ice, and there's 1, 2, and 3. And there's a bonus detection. We also detected a very strong CO2 and the CO emission. Okay, so let's zoom in a bit. Okay, so yeah, there's no question this water ice is detected. And more importantly, we detected this sharp feature, that's Fresnel peak. So yeah, there's one here, it's very sharp, it's another one. Okay, so problem solved. Comets are made of crystalline ice, so solar system form hot. But things is never that simple. As we get more data, and it turned out to be very interesting. So we got more objects. Another second object observed is 2019-03. And you can see these 2 objects observed at a very similar heliocentric and geocentric distance, but they show quite different behavior. First of all, that we only detected the CO emission in 03, and there's no CO at all. And that there's nice Fresnel peak in E3, but there's nothing. So most likely the O3 is made of amorphous ice. Now we're back to square one. We don't know what comets are made of. But we have a CO emission, and as Sarah showed nicely yesterday, they detected some CO emission in a Centaur 29P, and we see some similarity between these 2 objects. But in 29P, the CO line is stronger. And in 29P, as Sarah presented nicely yesterday, there's a variation observed in the CO and CO2 line profile. We actually observed a similar variation in the E3 spectrum, that CO2 emission line shows more symmetrical profile, whereas we see more variation of CO looks like CO is coming from a more confined region. So as Sarah concluded that 29P maybe consist of this the nucleus is consists of different parts forming different regions. So we think it's quite likely E3 is also has a heterogeneous nucleus. Okay, so now we have this CO and CO2 measurements. We want to compare that with other measurements of known comets. So Harrington-Pino et al., they compiled CO and CO2 observation of 25 comets. But you can see that most measurements are made within 5 AU. And there's one green dot there, that's 29P, and they divide their comets into two categories. One is a CO dominated, and a bottom is a CO2 dominated. If we put our measurements on this plot, guess where they would land? So they are here. So this is at 10 AU. That E3 is clearly CO dominated, and O3 is no CO, it's purely CO dominated. Okay, so we don't have that many measurement of comets, but we do have measurement of other objects in the solar system. And with our limited data, we already see a large variation among comets, and a similar variation has been observed in other solar system objects as well. Here I show this observation of trans-Neptunian objects. On the left is cold classical objects. On the right is Plutinos, and you can see they show different profiles and the different strengths of various absorption features. So what does this mean? Here I show you the formation regions of various comet groups. The Oort cloud comets are coming from between giant planets, and Jupiter family comets are coming from Kuiper belt. So as Sarah mentioned yesterday, we think this large variation observed, it's indication of a strong radio mixing early in our solar nebula. Okay, so what about future? Now we only have handful observations of distant comets and already see large variation. And luckily that LSST will be up running, and expected 10,000 comets will be detected. And as showing in this nice simulation, that hundreds up to 1,000 distant comets beyond 5 AU will be detected and characterized by LSST. And with these new detections, we can study their water ice composition, their volatiles abundances, and more, we can search for these PAHs. These have never been searched with JWST, and then people are welcome to put in proposals. There's a very exciting, interesting molecules to look for. And as Sarah showed yesterday, for strong gas emissions, we can search for isotopes. And just briefly mentioned, we can also study this object in the mini-infrared. They show rich spectral features, silicate features, water ice features, organic features. And so the future is bright and exciting. So here's a take-home message. So I'm happy to answer questions. Thank you.
Thank you very much, Vin, for this very nice talk. Is there any question?
Hi. You're talking about the detection of crystalline ice on the surface, but even for the distance of these objects, I guess that the temperature on the surface is enough to transform the amorphous size into crystalline one.
Well, so this is
the question is whether you would expect to detect any amorphous size when it might already has been transformed into crystalline.
This one is we actually choosing these objects. We calculated the transition temperature, transition period is going to take 1,000 of years for them to transform. So then we think there's not enough time for them to really have this transition in the coma. The thing is, we cannot really observe the surface feature. What we can see is just sublimated ice in the coma, but we don't think there's any chance for this object to, the transition can happen in the coma. That's the reason we choose these distant objects.
Hi, Ben. So nice talk. So I wanted just to back to the slide when you compare these two comets, O3 and E3 with the Olga data.
With
yeah.
Well,
Yes. This one.
Yeah.
So it's interesting. So we say that this is our two distance comet, but they are different two dominant molecules. So it seems in Olga paper that there is like some kind of trend.
Yep.
But here is like O3 is really out of that. So I would say maybe E3 is still like in that above of the line. But what's going on with O3? So is there's any you observed any particular other feature in the spectrum? What's going on with this comet? So
yeah, for E3, the ratio depending on what model you use. But for O3, there's nothing to debate because there's no detection of CO.
Oh, yeah, this is upper limits.
So that's solid evidence. This one clearly dominated by CO2.
Okay.
Yeah.
We have time for a very last quick question. Anyone else? What about online? Do we have any question online? No? Okay, let's thanks Vin again.
Thank you.
And the next speaker is Ian Wong. It will be an online talk. Hello,
Right,
Ian.
Hi.
Yeah, welcome. So the floor is yours.
All right, thank you. Yeah, good afternoon, everybody. Sorry I couldn't make it in person, but I'm really excited to share some new observations and results from the JWST mission. I'm sure many of you have heard a lot about these new exciting results over the past few days. But today I really wanted to focus on the outer solar system. It's sort of been a theme in this session. But I believe that we can argue that the JWST mission has been particularly impactful for these small icy bodies, really opening the wavelength range and sensitivity to more detailed study of these objects. So looking back at the history of spacecraft observations of these objects, we have these two end members from the New Horizons missions. We have Pluto, it's the massive object at 2,400 kilometers diameter, which with very exquisite, detailed surface modeling, a lot of very complex physical processes going on the surface. And then on the other end, we have the cold classical object Arrokoth, which has this unique bilobed shape, but at a much smaller, more than 2 orders of magnitude smaller than Pluto. So there's a question of what is the diversity that we can see in between these two end members, the 2 orders of magnitude of size. And we already know from ground-based observations that Kuiper belt objects have a stunningly diverse range of colors, albedos, as well as detections of volatile ices. So in the first 2 years of JWST science operations, more than 80 KBOs have been observed, and they show a stunning amount of diversity in their spectral features. And this has mostly been enabled by NIRSpec IFU, which provides continuous coverage from about 0.6 to 5.3 microns, opening the space for the detections for new volatile ice species and other surface processes. So there's an important distinction to make here, and that is as a function of size. So for the largest KBOs, their gravity is strong enough so that they can retain hypervolatile ices. These are CO, methane, and nitrogen. And for example of this, I'm going to turn to Triton. So Triton is the large irregular satellite of Neptune and thought to be a captured Kuiper Belt object. So during the first year of science operations, Triton was observed as part of a guaranteed time observations program. And we obtained two different views of its surface, the anti-Neptune and the sub-Neptune hemispheres. Here you see the full spectra at high resolution. This is R of about 2700. And you can just see how spectacular the spectra are compared to what has been previously obtained from the ground, particularly in the region beyond 3 microns, which has previously not been probed from the ground or from near Earth orbit. So as I mentioned, these large objects are able to retain their hypervolatiles. And indeed, we see a lot of methane bands throughout almost the entire wavelength range. You see a forest of these methane band features. But in addition to methane, there's a lot more going on the surface. And this really shines the light on how exquisite JWST is in this realm, really revealing the diversity of these ices. So the star of the show for Triton is the amount of CO2 on its surface. It's really unique in having a very strong CO2 abundance, as evidenced by over 20 overtone and harmonic bands that we detect throughout the spectra, and I've indicated those in orange. In addition to CO2, 12 CO2, we actually have 3 other isotopologues that we're able to probe thanks to the coverage of this 4.2 to 4.5 region. Not only do we have 13 CO2, but we also have the very first detections of solid 18O isotopologue of CO2. So you have 12C18O16O and 13C18O16O. Furthermore, we have CO. This is not a new detection, of course, but we now have those primary bands at 4.6 and 4.8 microns, both 12CO and 13CO. And in addition, we have the detection of CO atmospheric fluorescence from the thin atmosphere that Triton has. So this just gives you a taste of the capabilities of JWST in this realm. But we really are interested in probing sort of what we call the garden variety KBOs. KBOs that are less than about 1,000 kilometers in diameter, which are thought to be more pristine. They're not gravitationally differentiated, and they are likely more primordial than these large, volatile-rich objects. So for this, there was a very, very powerful tool that we had in our toolbox, and that was this large Cycle 1 GEO program led by Noemi Pinilla Alonso, which looked at 59 targets, covering basically all dynamical classes and colors that we know from the KBO population, as well as some centaurs. And this treasury of spectra covering 0.6 to 5.3 microns in the low resolution mode of about R of 100 really allowed us to look at the diversity that we see in the Kuiper Belt objects among the bodies are of more typical sizes. So these covered somewhere from 200 to about 1,000 kilometers diameter. And what we find is that there are 3 distinct spectral classes among these objects. On the right here, we have an average spectra of these 3 types. On the top, we have a water ice rich type, which also shows some weak CO2. And then in the middle, we have a more CO2 dominant class with a very, very particular morphology in the primary band around 4.2 microns. These objects in the middle also show some evidence for perhaps methanol, as well as the emerging dominance of some organic bands, particularly in the 3.2 to 3.6 micron region. We also have CO ice, which we think is not primordial CO ice, but rather a radiolytically produced CO from the CO2 ice that's otherwise dominant on the surface. Lastly, at the bottom, we have this more complex class, which shows, once again, strong OH and CO2 ice features, but have some more spectral bands associated with more methanol, perhaps, as well as some minor features that may be due to nitrogen and sulfur-bearing species. So all in all, we see from these 3 spectral classes that there is evidence for at least 2 distinct compositional gradients within the primordial protoplanetary disk at these large heliocentric distances, suggesting that there was a lot of chemical diversity, as well as subsequent mixing that transported these 3 spectral types into all the dynamical classes that we see today. Okay, so what is the bigger picture? So in the history of solar system dynamical evolution, there's this emerging model, sometimes called a Mies model, the dynamical instability model, that posits that a lot of the middle and outer solar system small body populations initially emerged from a single proto-Kuiper belt, somewhere beyond the primordial orbits of the ice giants. And then after the dynamical instability, these split into kind of two groups. We have the modern day Kuiper belt, and then we have a number of Jupiter resident populations in the middle solar system, primarily the Jupiter Trojans are the most well-known of those. This, of course, is not a static system. We have continual dynamical evolution to the present day, which causes some Kuiper belt objects to evolve inward to become centaurs. We heard a little bit about that in the last talk. And then ultimately, they can eventually be transported further inward into the Jupiter region to become Jupiter family comets, such as 67P. So we can ask ourselves, can we use spectral characterization to try and tease out some of the chemical and physical processes that are underlying this roadmap of solar system evolution? So for this, we look at centaurs and Jupiter Trojans. So these are very useful because, centaurs in particular are very useful because they are essentially tracing what we believe to be the dynamical history of Jupiter Trojans during that inward migration phase from the proto-Kuiper belt to the Jupiter region. So in cycle 1, there were 6 Trojans that were observed as part of both GTO and GEO programs. Of these, 5 are targets of the upcoming Lucy flybys, which will take place over the next decade. And they also sample both of the color classes that we know exist in the Trojans. So in the top here, in this figure, I show the results for 2 Trojans. And you can immediately see that they have much weaker spectral features compared to similarly sized KBOs, which I've shown in the bottom. There is very, very little evidence at all of water ice. This is consistent with ground-based measurements for many decades. But they do show a 3-micron band. At least some of them show a 3-micron band that indicates OH. There's also evidence for organics at 3.4 microns, particularly on the red object Oris. And for Euripides, there's a unique weak CO2 feature at 4.25 microns. This is very contrasting with the KBOs, which show very, very deep water ice features, including the Fresnel peak we heard about earlier, as well as much stronger CO2 features. So we can ask ourselves, if Trojans are indeed from the Kuiper belt, they must have endured some sort of secondary processing. Right? What could have happened to transform those surfaces into what we see them today? So centaurs give us a little bit of a hint. So these are 2 centaurs observed from the large GEO program I mentioned before. And you can see that they show a range of water ice feature depths. And what's really interesting is if you look at their heliocentric distances, there appears to be a trend in which the closest in one, Okraho, has systematically weaker features than the more distant centaurs and ultimately the KBOs. So perhaps this is tracing some sort of coherent trend where in the secondary thermal processing of these objects is attenuating their features and ultimately, with enough time, could transform KBOs into a spectrum that looks like the Trojans. So what else could be happening? And we heard about this in the previous talk, and that is activity. So centaurs, a subset of centaurs are active, and this transforms their surfaces in many different ways. So during the first 2 years of JWST science operations, about a dozen active objects have been observed. And here's an example of one from my own DDT program from cycle 2, showing Chiron, one of the most well-known centaurs. And here you can see some very, very interesting features. This is perhaps the first example of a CH4-dominated activity. So we see evidence for CH4 emission, as well as CO2 emission, and curiously, no CO. We don't see evidence for CO, unlike previous detections of CO at shorter heliocentric distances. And what is really fascinating about this particular epoch of activity is that it is at 18.8 AU. This is by far the most distant report of activity on a centaur, comparable to some of those dynamically new objects that Bing Yang just presented. In addition, we see a surface that has very, very strong CO2 ice features. And this is very distinct from other similarly sized KBOs and suggests that there's production of more pure CO2 ice grains thanks to the activity. And indeed, from spectral modeling of the features at 2.6 and 2.8 microns, we see that we are dominated by these micron-sized grains, coated grains, or aggregates of H2O and CO2, which is very distinct from the inactive Centaur spectra that we have seen previously in the previous slide. So this really gives you a taste of the immense diversity and the surprising features that we're teasing out now with these with the spectrum of J2ST. So what does the future hold? We will always be looking for more objects. Now, we already have 80 objects of this type, of course, but looking for ensemble trends will be very important in teasing out perhaps where the transitions in the Kuiper belt were primordially, and also looking for other subclasses, spectral subclasses that could tease out some of the detailed evolutionary processes that are going on in the past and up to the present day. So with that, I'll end and take some questions. Thank you.
Thank you very much, Ian. Any question? No? Okay, let's thank Ian again, okay, for this very nice talk. Good, so let's move now with the next speaker. It's Denis Bodevitz. He's going to talk about the first detection of water vapor surrounding a main belt comet.
So being here in this meeting, I feel kind of sorry for my title. Like essentially every James Webb title is first detection of, and then you insert your favorite gas and your favorite objects. Can you guys find it? Yeah, there it is. So in that sense, first detection of water in a main belt comet. Yes. So I'd like to continue on what Ian just told you, and that is that I think that the major breakthrough in the field of small bodies and planetary science is that we're finally able to connect all the different populations. Ian was talking about centaurs, about KBOs. We've seen comets in the talk before that, and I'd like to confuse you even more in that it's actually really hard to also distinguish asteroids and comets. So students like things to be simple. So in my classes, I need to explain what is a comet, what is an asteroid. And it is the infamous IAU meeting a few years ago where planets were defined, and famously comets and asteroids are not defined. And that was a wise decision because it's very difficult to explain the difference. So simple picture here, comet is a dirty snowball with a long, narrow orbit, a highly elliptical orbit. It supposedly is formed far away from the sun. It gets fiery tails when you heat it, and it was the main target in the Deep Impact movie, and also the mission, which I worked on. And an asteroid is much simpler. It's a lifeless rock, rounded orbit, forms closer to the sun. It has no tail, and in the simultaneously released movie, that was the target of Armageddon with Bruce Willis. So let's have a look at that. It doesn't work that way. So there are comets with no tails, many of them now. Some of them have dubbed those, Karameses have dubbed those Manx comets. Manx is a cat with no tail. And so these objects are on hyperbolic objects. They even seem to come from the Kuiper, from the Oort clouds. But when heated, when getting close to the sun, they don't show no evidence of a tail, or rather of sublimation activity. So when we talk about comet activity, it really means sublimation. So some ice, some volatile is turned from ice to gas. And then in the asteroid belt, there are plenty of examples of objects that show what looks like to be activity. So an asteroid with a tail. I think the most famous case is now DART, of course, Didymos, the asteroid that was impacted by our spacecraft, and it formed tails. But it also happens naturally. There are a lot of collisions in the asteroid belt. There are objects that are rotationally sped up and start to fragment. There are several processes through which you can get objects like the ones you see in these pictures. These are all asteroids. However, there is a small subset of asteroids that do this over and over again. So either those would be the most unluckiest asteroids you could find by being repeatedly hit, or something else is going on. And we think it's the latter case. So for about a decade, if I'm right, we've seen those asteroids, most famously 133P, that's the one in the right column in the middle, El Spizarro. We know that every time it goes to perihelion, it gets a tail. Second one that was discovered is just below that. It's a tiny little image, 238p, and that's the object that I'm talking about. And so this repeated activity, we always thought that the only explanation for this was that you have to have some sublimation process that drives off dust in a coma, just as it were for a comet. However, this happens in the main belt. Those objects have been there for a long time. So it raises a lot of questions. How can you preserve water ice so close to the sun? Now, we wanted to know badly what drove this. So people have thrown a lot of resources at discovering this. Hours and hours, and days of telescopes like VLT, Hubble, everything. And you know where this is going. In 1 hour of James Webb time, we were able to resolve this. So let me just say a couple more things about 238p read. So this is a diagram from a paper by Henry Shea from 2011. And all those color dots are indications of when this object was discovered to have dust surrounding it. So again, we could not detect gas directly. It was too far away, and we didn't have James Webb. But you could see that there was a tail or a coma. And so that's pretty consistently. So you see that this is 2005, that's the green dots, and then again in 2010. And then outside a certain distance from perihelion and on its way to aphelion, the activity stopped. This object is not an intruder. It's not a comet that was captured in the main belt. It's been there for at least 20 million years. And it also has an inclination that suggests that it was formed there and always there. Yeah, so here's the James Webb data. So first with MIRI. So on the left in blue, you see that this is an object that looks like a comet, right? It has a big coma, big tail, moving away from the sun. So all the physics that are usual. And then in the right, this is an image where we use one of the filters that includes the water gas emission feature. And so that's a little noisier, but you can clearly see that there is an extended coma of water there. I put the numbers down there. So this observation was done in September of 2022, about 100 days, so 3 months after this object's perihelion. It's 2.4 AU away from the sun and 2.1 AU from Earth. And so those numbers are important because 2.4, 2.5 AU from the sun is about the distance where you can easily sublimate water. If you're going to go much further, temperatures are just too low, and the ice would not effectively sublimate. But show me the spectrum. Here's the spectrum. This is again the IFU. So you see between 1 and 6 microns. And in the white is the spectrum of this main belt comet, 238p. And for comparison, I show you in blue the spectrum of Hartley 2. This is a spectrum that was acquired by a spacecraft. So before we had James Webb, this was a deep impact spacecraft that, as a secondary mission, flew by Hartley 2. So there's similarities and there are differences. So first have a look at that water. The water feature is very clearly, I won't use the pointer because people online can see it, but just below 3 microns, you see this strong emission feature of water. And this by itself was so amazing for us because we knew, well, we suspected that there was a volatile driving it, but after all these years, to get this strong of a signal in so little time was just amazing to see. This is, as I'll show you later, this is the equivalent of 1 cup of water, 300 milliliters per second, that you spread out over 100,000 kilometers. And you can see that with James Webb with no issue at all. And now the other surprise is the lack of CO2 emission. So you've heard this many times now. James Webb is incredibly good at finding CO2 everywhere, but it's not there. So you see that in Hartley 2, there was a lot of CO2. CO2 has a big fluorescence efficiency. It's pretty easy to detect if you have the right instruments. But what we find is that 238p actually has the least amount of CO2 in any small body that we've ever observed at this point. At that point. So here are the numbers. Comet people are funny. We talk in molecules per second. So these are really, really weird numbers. So 10 to the power 24 molecules per second. That's that 1 cup. This is about 4 to 5 orders of magnitude less than what you see in a normal comet. So it's a really tiny, tiny amount. And that's why only James Webb can do this. So the constraint on CO2 is even stronger. So it's about a factor of 100 less than the water. So less than 3 grams per second. Also, this is a really, so going forward, this is a really small object. This object has a radius of about 0.24 kilometers. So even for comets, it is very small. Now, what you can do is we understand the physics of ice, right? If you have ice and you heat it, it's going to take a certain amount of energy to convert this to gas. So what you can do is treat comets like solar panels. You can say, like, I'm producing so much water vapor, and so therefore there's got to be an icy patch on this object of a certain size. We call that the active area. It's ignoring a bunch of physics, but as a first order of approximation, it is fine. So what you get is that this is a small spot, like 0.03 to 0.11 kilometers square, depending on your assumptions on albedo and how the object rotates and redistributes its temperature. It's small, but again, this object is small, so this would be about 4 to 15% of the surface. Now, that's not unlikely for comets. Most comets are around 4 or 5%. However, because this spot is so large, it means that the ice on this object is likely not caused by an impactor or uncovered by an impactor, because it's large enough that this would have been catastrophic for this object. If you need to create a patch that big, you have to hit the object really large. So that means that the ice must have been there. It's endemic to this object. And then there's the second thing. If you do the orbital integration, so you assume an activity level throughout the orbit and you integrate, you find that you lose about 3 million kilograms of ice per orbit, or enough to cover the entire thing by 1 centimeter of water ice. That's a lot, and that is about the same as the erosion rate that you're going to have of what that water ice is dragging the dust in. So that means that this cannot last. The ice is going to retreat faster, and after a few orbits, we will expect this object to no longer show this activity. So, in formal speech, the near surface layers devolatize on orbital timescales. Then this, going back to that CO2. So this is a collection of comets, and similar to the plots that you've seen before, this is the abundancy of CO2 versus water as a function of heliocentric distance of where comets were observed. And I think it's pretty obvious which one is 238p Reed in this plot. I put a big red star on it. This object is more than one, almost 2 orders of magnitude depleted in CO2 than any other object we've ever studied. And that makes sense. If this object was indeed stable at the orbit where it is, and it's been heated for so long, then the CO2 must have retreated way below the surface, and it's probably gone from the object entirely. Because CO2, dry ice, has a much lower sublimation temperature than water. So, just to wrap this up, first observations of a main belt comet. Main belt comets are fundamentally different than regular comets. So there's obviously water that is driving the activity, and this makes sense and explains the recurrent activity. Evolutionary, it won't last, so that's why we don't see water activity from all asteroids. The CO2 is a big puzzle. It was heavily depleted. Really good upper limits that we found, orders of magnitude different. So it just means that this is a fundamentally different class of object with a very different evolutionary history. And it implies that we have a reservoir of water ice nearby the Earth, which is of course astrobiologically relevant. So just to give you a little look into the kitchen, we've since then observed 2 more main belt comets. One is the most famous of them all, Elst-Bizarro. This was the first main belt comet. And the second one is 358p Pan-STARRS. And same results. We get even more constraining results on the CO2. They are bone dry in CO2, and the water signal is whopping. So this is really a big class of objects. And as I sort of jokingly start in my first slide, I think this is really exciting because we're starting to find differences and similarities between all the populations of small bodies in our solar system. That's all that I have. Thank you.
Questions? Yes, we have one there.
Hi, Dennis. Joe Newth from NASA Goddard. Do you think that the interior of those main belt comets could be just barely warm enough to sublime a reservoir of water slowly to the surface, and it really takes the surface to be heated in order to allow it to flow outward?
Yeah, I like that. What we've learned from Rosetta is that comets, even as small as they are geological objects, and the storage and release of volatiles is extremely complex. What you're going to get is that you have a heat wave going inwards, that what you just said, volatiles move outwards, but maybe by the time that they get there, now the object is far enough away from the sun that it's cold again and they freeze out near the surface. And the moment you switch it on, they go. I think that happens more with hypervolatiles. So oxygen, molecular oxygen was the most famous example of that. I think water is not volatile enough to really get it down from the deeper layers. And this object is also very small, 250 to 240 meters in radius.
Hi there, Nick from the SO. So you showed some historic detections of this water ice, but how far back has it been detected? Because it seems like it must have been a sudden event that caused this, right? And you were saying that this patch, it wasn't an impact or something.
Yeah, that's the $1 million question. And so, you know, this is the first time we can actually discover gas. Before this was just inferred based on repeated activity. And so now we know it really is water. It was a difficult paper to write in that sense, because we confirmed what we had already thought. It was not, but anyway, that's the details. It seems that the activity is decreasing with every apparition, and that will be consistent with a volatile layer being depleted. And then we did not speculate on the causes of it. We only concluded that had it been an impact, it would have been way too disruptive. The small object would not have survived it. So it's more likely that there is just a reservoir of volatiles in the main belt.
Yeah, thank you for the talk. My question was also about the impact, because this kind of seems like the obvious reason for this kind of event. Because, but what I wanted to ask is, if this is an impact, can we assess the population of such objects? So if we observed one such object, and then we can calculate how many collisions of this kind can happen, and do we expect another object of this kind to be found?
Yeah, so I think there's now about a dozen of main belt comets. So yeah, it's a number of games you could do, especially now that we know or we provide a measurement of how long the activity would last. So it becomes like a long equation with probabilities, right? So yeah, it can be done.
Thank you.
Thank you very much. Last question very quickly.
Yeah, I guess I was just going to say, as a follow-up to that there are additional processes that could spark that. It needn't just be an impact. It could be spin up due to Europe or something that would cause you to shed material. So I agree with you, Dennis, that it would be there's lots of things going on. It might be difficult to tie it directly to a rate.
Yeah, the problem is thermal diffusion. It's the small bodies are very porous, so the heat doesn't happily transfer deep down. So you need something to spark that. And my time is up. So
Fine, let's thanks Dennis again. Our next speaker is Colin Snodgrass. He's going to talk about the Comet Interceptor mission.
Okay, yeah, thanks very much. Yeah, nice to come and tell you all about Comet Interceptor. We've been learning all about what we can do observing comets with JWST, and I promise we will get some JWST in this talk. But the other thing that's nice about solar system objects is you can go there and you can actually go and get resolved images and in situ measurements. And so for comets in particular, this is important because this is the only way we resolve the nuclei. These are small objects. With JWST, we're not going to resolve the actual shapes of them. And this is how we can measure directly with mass spectrometry composition, and we can compare that with the spectroscopy we get from JWST and others. And of course, we can also measure how they interact with solar wind and all these other things that you can only do by going there. And this slide shows some images of the nuclei of the comets that we've visited with missions to date. And the thing to note about these is they're all short period comets. Even Halley, that goes around every 70 odd years, this is a short period comet. It's been past the sun many, many times. And so what's different about Comet Interceptor is the fact that we're going to try and target a new comet, something coming in from the Oort cloud, something that's not seen the sun lots of times. And the reason why we want to do this is one of the things that we learned, particularly from Rosetta, is that actually you get a lot of dust falling back onto the surface of the comet, as well as the material leaving the surface and eroding away. So all of the comets we've seen have evolved. They are not these pristine lumps of the protoplanetary disk that we like to think of them as. By the time that we've seen them with a spacecraft, they've been heated many times, had lots of cycles. And so the idea is, let's go to a long period comet, something coming in from the Oort cloud, something that's not seen the sun nearly as many times, if at all, since the sort of early eras of a solar system when these things were forming. Now, there's a reason, though, that we've always gone to short period comets before, and that's because a long period comet is a difficult thing to target with a spacecraft. The only way we can do this is to discover one of these things coming in and get, with enough warning, to get a spacecraft to it. You know, these things have orbital periods of tens to hundreds of thousands of years. We don't know of any that aren't already past us and gone away. You know, it's longer than we've been doing astronomy. And so you have to find one coming in, and then you have to react and you have to get there. And typically we've been discovering these comets as they're entering the inner solar system, as we've been saying, when at the kind of 3 AU distance where water ice starts sublimating. This is where they get really bright. And so we typically detect them then. But on a long period comet orbit, the difference in time between something crossing 3 AU and then coming close to kind of 1 AU and the Earth and coming into sublimation and region there, you have months. And that's no time to, you know, convince a space agency to give you a whole lot of money, build a spacecraft, launch it, get there, and so on. We've been hearing about Via Rubin Observatory and LSST quite a lot in various meetings during this week. This is going to be an amazing facility that's going to discover comets further out. We hope to find things quite regularly, kind of when they're approaching and their activity starting out 10, maybe 20 AU. But then we still only get a few years warning time, and not the, you know, a decade or so that it can take to get a spacecraft built and launched and into the right place. So how do we do this? With Comet Interceptor, what we do is we build the spacecraft without knowing what our target is, launch it into space, and then just kind of loiter around until we spot a comet that we like. And conveniently, the first F-class call from ESA, so this is a call for fast class or flexible or whatever else you want the F to stand for. These things are, this was a call to go and have a rideshare launch with the Ariel exoplanet telescope, which is going to the Sun-Earth L2 point. This is where JWST is. It's a popular place to park your space telescope. It's also a good place to park your comet hunting spacecraft, because you can sit and station keep there for quite a while with relatively little fuel and be in position when you spot a comet that you like to set off and intercept it. So this is what Comet Interceptor does. We launch with Ariel, we go out to into a halo orbit around the L2 point, and we'll wait there for potentially up to a few years. While we're doing this, we're searching for the sky for comets with various surveys. Most likely LSST will be the one that finds it as the, you know, the powerful new survey that's coming up in the next decade. When we spot a comet that we like the look of that's going to the right direction, we can go and figure out where its orbit's going, find out, okay, this one's going to cross the ecliptic plane close to Earth's orbit. This is where we can get to with the sort of fuel reserves on board the spacecraft. We predict where it's going to be and when, and we go, okay, we can get the spacecraft there, fire the rockets, head off and head towards an intercept while we're monitoring this comet inbound with various telescopes and studying it. And then we have a fast flyby as the comet is crossing over the ecliptic plane, somewhere near 1 AU from the sun. Now, the spacecraft is also novel, as well as being the first time we build a spacecraft to go somewhere where we don't know the target before we launch. It's also the first time we go and take a multi-spacecraft mission to a comet, which is also a neat thing to do with a cometary mission, because it allows you to make measurements in different places within the cometary coma at the same time. This is going to be a fast flyby mission, so it's not going to be going into orbit like Rosetta did. We can't spend years studying the comet. We will get a few hours of measuring data as we fly past it, but we can measure from multiple places. That means you can actually find out within this coma what is spatially varying versus what is changing with time. That's something we couldn't even do with Rosetta, because, you know, Rosetta, it took some time to get from one side of the comet to the other as it orbited. So you didn't know if you measured a different composition on one side versus the other. Was it that the comet had changed in the meantime, or was it just that changing with time? So it's nice to be able to do this multi-point measurements. It's also very useful for a fast flyby, because it means that the main spacecraft can have a relatively distant flyby, and we're going to go past around about 1,000 kilometers from the nucleus, give or take, where we are passing through the coma, we're passing through all of the dust grains and the gas in the coma, but we're not going in the very inner coma where those are going to pose a lot of danger to a spacecraft. But we've got these deployable probes, which are expendable. We're not expecting to get them back. We're not expecting them to work more than 24 to 48 hours. And so they're launched in trajectories into the very inner coma, and then they're sending back data from that to the main spacecraft. So we can combine this kind of safe approach of the main spacecraft surviving the flyby with this kind of high risk, high reward strategy of launching the small spacecraft close to the nucleus. This is a nice diagram from ESA that shows the three spacecraft and the collection of instruments we have on board. We have a high-resolution camera on the main spacecraft, which is actually based off of the Cassis imager, which is currently in orbit around Mars, taking wonderful images from there. So the highest resolution images actually come from the main spacecraft, even though it has the distant approach, because it's a real telescopic camera. We have MIRMIS instrument, which is spectroscopic and imaging instrument through the near infrared, so that's going to give us lots of composition. And we have a mass spectrometer that's going to give us composition in situ by measuring the coma, the gases that we're passing through. And then we have a whole suite of instruments that are part of sensors that are part of one instrument called this DFP package, which is looking at the plasma environment, the dust environment in the inner coma. On the smaller probes, the B1, which is actually the JAXA contribution. So the whole probe and the instruments on this are built by our Japanese colleagues as a contribution to this ESA-led mission. And so this has two different narrow and wide angle cameras for looking at the nucleus and inner coma. It has this hydrogen imager, which is looking at the Lyman alpha emission. So it's looking at the UV at the coma and its structure, and also being able to measure the amount of outgassing from the comet and even D2H ratios. And then it also has its own plasma instrumentation on there for comparison with the other two spacecraft. And then the B2 is the small European spacecraft. Again, it has other components of this plasma suite, making these multi-point measurements in three different places. And it also has a polarimetry camera, ENVIS, which will scan the whole sky and give you dust properties, and a forward-looking periscope that will get a view of the inner coma and the nucleus, looking around the dust shield on that spacecraft. So that's a quick tour of the hardware. This is currently, people are working on instrumentation, putting this together. The other thing that we're doing at the moment is that the science teams associated with the mission are preparing. So there are two major working groups. One is on studying the comet and the environment and making model predictions and looking at what we're going to measure. And the other one, which is one I'm going to tell you about now, is the target selection group. The people involved with this are listed on the right-hand side there. Currently, I'm the chair of this, and Seiji Sugita from University of Tokyo is the deputy chair. This group is tasked with trying to actually identify a target, which is quite important for a space mission. And we're launching not knowing what our target is, potentially. And so at the moment, this group is advising on targets. So what we're doing is we're studying any comets that are potentially look like targets we can reach. Anything we're discovering now, it's too early. The mission's not going to launch for a good few more years. So anything we find now is we describe as a virtual target, one that if we were already in space now, we could visit, and as a good kind of practice and a good way to study this comet and think about how would we do things in a few years' time when we have to do it for real. But also defining how do we make decisions. If we're in the situation where we have, 2 or 3 comets, which one do you pick? You don't want to have that debate just at the time. You want to think about that. So we've been thinking about how to prioritize targets. And, preparing in general for tools for LSST era, making predictions, getting ready. The sort of short version of our prioritization scheme is that, if we get some interstellar object that by chance is going somewhere we can reach it, then the whole team agrees, yeah, let's go and get that because that's such a unique opportunity. But it's also incredibly unlikely, so we're not going to worry about that. What we want to do is we want to ideally look at a comet that's coming in for the first time. So if its orbit suggests that this is dynamically new versus a returning long period comet, that would be preferred. And then we also have some preferences for the encounter. So if you have something that's a highly retrograde orbit that would be a very high speed encounter, that's not as good as something that's where we can meet it a bit more slowly. Just gives us more time to take observations, and it makes it a safer encounter in terms of dust velocities. But then otherwise we would like to go and see, high level of activity so that all the in situ instruments can measure things. And then just lastly, one of the things that we're doing is we're looking at virtual targets. And just because this is a JWST session, I promised I'd mention some JWST. Here's a hot off the press JWST spectra of another inbound long period comet. This is 24E1. So this is one that's, one of these virtual targets. It was discovered at relatively large distance, about 8 AU. It will come into perihelion inside of 1 AU in 2026. It would have been marginally possible for us to reach this one. It's not a great target. The encounter will be on the other side of the sun. We don't really want to do that. But it's a good example to practice the prioritization and to think about how would we like to study these things. And in particular, this one's given us a good opportunity to request and be granted JWST time to observe this thing at different distances from the sun as it's inbound. So this is the first spectrum required when this thing was about 7 AU from the sun. You can see it's got sort of absorption features, probably water ice. There's some CO2 there. There's not obvious CO. But this is, we're still looking at this spectrum. And the nice thing is we're going to go back to this next year and get 2 more observations as this thing crosses the water ice sublimation region. So we should see how these spectra evolve, which will let us make better decisions about where to point the spacecraft. Okay, so just to wrap up, we're selected in 2019, finally approved in 22. We launched in 2029. Here's some photos of some actual hardware on instruments that people are building. And yeah, we're going to fly past a comet at some point in the 2030s. And I'll stop there and take the questions.
So we have time for one quick question.
Hello, Cornelia. Thank you for your talk. So my question is, as I understood, you have like several years only for the spacecraft around this point. So, did you estimate how many objects in general you should expect in this time interval? So maybe the average number based on some, models, distributions.
Yeah, so one of the things we had to do in the proposal was to look at the statistics and make a reasonable argument that, yeah, no, there's a good chance this is going to work. And the short answer is yes, there is a good chance it's going to work. We are unlikely to have a very large number of comets to choose from. So our prioritization exercises are kind of wishful thinking a lot of the time. It's likely that the first good target we spot, we will go for. But yeah, we can wait. With the whole mission can last up to 6 years, which is primarily dictated by the funding environment. And so we can wait for a few years looking for, do we see a good target coming? But yeah, the rate of comets arriving is a good chance that we get one.
Thank you.
We have one online question.
Yes, from Garrett Williams. So how close to 1 AU do you need the node to be? What fractions of LPC long period comets have nodes within that range?
Yeah, so we can meet a comet more or less between about 0.8 AU from the sun out to about 1.2. That's largely dictated by spacecraft thermal constraints, but also available fuel. So, it has to pass roughly within that kind of range. And yeah, as I said, it's basically the same as the previous question. There are enough comets that pass through that range that over the course of a few years' wait, we expect one to pass through the right region.
Thank you very much, Colin. Let's thank Colin again. So our last speaker of this session is Joseph Moulin. He's going to talk about implementing an astrolab project in Africa.
Hi, everyone. So my name is Yusuf Moulin. I'm from University Mohammed VI Polytechnic in Morocco. And today I'm not going to be talking about science. So if you would like to, I have a poster about Comet 29P. We were talking today about distance comet, and we are trying to we are going after CO plus with telescope SOAR. But today, since you know that in this symposium as a talk, we decided that we include also the outreach part. And as you can see, for the last of a session, we got the outreach and education talk. And this is, I think, is good for the community since we have in this first International Union Assembly for the first time in Africa. But today, I decided I will give this talk about the outreach, and I'm going to talk about a project which is not done yet, but we are trying to do that in Africa, which is I used in the title, Implementing an Astrolab Project in Africa. So let's have the context and why I'm motivated and interested in this project. So this is the situation of the astronomy in Africa. You have as you can see on this map, so different colors. So the green, that only the countries that can publish one more paper per year. But those who are in the yellow, they are publishing less than one paper a year. So in the countries, and you can see also the situation of the observatories, the professional observatories in Africa. So the circles with dot circles with the full circle, which is the countries that have a professional observatory, while the others they have some plans to build observatory, a professional observatory in their countries. And also as you can see, which countries that they have a space agency. So I am sure that this is, if we use that map, if we have similar map of Europe or for US or for America or for Asia, so it's not going to be the same. And that's what we are having, this lack of astronomy activities in Africa, and we decided to try to come up with some project that we can motivate younger people to be to go to do science and do astronomy if they love to do that. So what was the motivation behind that is to try to significantly contribute to development of digital education, because this is going to be an online lab. So we don't need to go to countries because it's going to cost money. But of course, we are doing that with other organizations like African Astronomical Society, organizing schools and doing some workshops. But this one, we decided to do it in a digital way, as today, we have everything. So we can connect people from everywhere in Africa to do some online labs. So this is going to be to inspire and engage students. Does not mean that students they might like it, they might not, but we will encourage them to come to this online lab to do some, to conduct some astronomical research and education through some remotely accessed telescope. And with that, I would like to thank the LCO network, who are providing a number of hours, which I'm going to talk and be in details, to the communities in Africa and around the world to use their telescopes, small telescopes, because in this kind of labs, we don't need 10-meter telescopes, but we can use small telescopes to do a lot of education and outreach activities. So, and this, of course, to address the lack of astronomy infrastructure that we have in certain regions, as you can see here in the map, and this maybe can implement some students to begin in some hands-on experience and to do more astronomy. And most importantly, so in Africa, we are diverse. So we have some countries who speak Arabic, others speak French, others speak English. And this is also, we take it in consideration to be more accessible and inclusive. We're going to provide this program in 3 languages. So I know it's going to be hard, but we will find people who can train the students in English or train them in French or train them in Arabic. And the call is open to everybody here who want to help with that. So he just contact me, and I will be happy to chat about this project that we are trying to do. So the lab will be online lab, so we will be do a lot of things. So first, we will train students to do observations, how they can plan their observation with remotely telescopes. So, and most of you maybe, I will talk about the LCO telescope, network telescope, which is cover all the region of the world. And we will do also providing some training, how students can reduce the data and working on projects. I will talk more about that. And also we will give students and sometimes also teachers some educational resources that they can do some activities by themselves. And why not to contribute to science? And this is the goal.
So to have the student trying, getting trained, getting doing activities, and then at some point, why not, they are participating in papers. And we have some examples about that from Africa, but we want to make it in a large way. So as I mentioned, we were going to be using a program called Global Sky Partner, which is LCO providing, which is an educational program using like more than 10 telescopes of 0.4 meter around the world, as you can see here in the map. And LCO is providing more than 1,000 hours just for this program. And the idea behind that is just to encourage the activities on astronomy in the front places where there is lack of astronomy. And we really appreciate, they're not giving us 1,000 hours, but they are giving us some time, enough time to run this program in Africa and so on. So this is how this telescope looks like. So this is our remotely accessed telescope. So we don't need to go there or to bring student there. So students will be connected to an online platform when they can see the teacher or training them how they can do observation. And at some point, the student, they will be able to do this observation by themselves because the LCO, thanks to them, they are making a really easy web page where students can fill all the information regarding their targets, regarding their watch filters, for example, they're gonna use. As you can see here, they have a bunch of filters that they can use, and they can do different science cases. And on the way, I will highlight some of them. And also we have another alternative observatory, which is Camden Observatory. So we have a bunch of telescopes there, all of them also remote telescopes that we maybe can use for this project. And thanks to Zuhair, who's the director of the Camden Observatory, for providing us and providing the community this possibility to use these telescopes at the Camden Observatory and to help Africans to get access to astronomy. And also, again, the call is open to everybody who wants to have like some access remote telescope that we can help this with the program. Please reach out to me, and I will be more happy to chat about that, and we can give this hand to African students to learn more about astronomy and do astronomy research. And also at Camden Observatory, which is not included in the picture, we have a really small, because that's what all we need. We got some amateurs, they got telescopes on the Camden Observatory, and also they're offering some time, and also they can help us to get some time on the small, tiny telescopes, like there are 20-centimeter telescopes that we can use for this project. And thanks to this collaboration of the High Atlas Observatory, which is like this association in Morocco, they are also building telescope from their pocket money, and they are offering also this time to the community that we can use and get some observation and get some training for Africans. So we are trying to, in this project, this is not a final decision yet, but I think they are more than happy to help us on that project. So what can students learn from this online projects? So we can do a variety of projects, as you have heard yesterday from different talks. So we can do exoplanet transits, and we can participate in some citizen science, as you have seen yesterday highlighted in some of the talks. So we can do variable stars observations. So this is easy thing we can do with small telescopes. So we can do some transients and supernova monitoring. So for students, but we will be focusing more about the planetary one, which is I'm expert in, and they can help with, but this is open to all other science cases. We can also search for asteroids and comets. I know that we'll be doing good as LCST, which is the job to do that, but we can help students to find in the data doing this kind of discoveries, and we have many examples about that amateurs find a comet and asteroid, and one of the big ones is to Borisov, which was discovered by an amateur guy. So I can also do characterization of the small bodies objects, including asteroid and comet. So we have time students can do this kind of object, and why not maybe cannot even contribute into some papers by providing some data from the telescopes. So the idea behind that was also to participate in some of the citizen science projects. So unfortunately, we have a lack of the citizen project in Africa. So we know that Europeans and our colleagues in the USA, they have, and especially NASA, they have some programs, but we can also participate in programs even if we are not based on these countries. So, and they are offering some trainings, and also I'm in touch with them. So like Exoplanet Watch or Planet Hunters test, and also some citizen science like discovering new asteroid or active asteroid in some of the telescopes database. And we're gonna try to train students how they can do that collectively or individually. So here are some examples that we can do for this planetary science citizen projects, sorry. So like transit, and this is one of the examples that amateurs are doing. So our colleague from High Atlas Observatory, Condé Observatory, orders some nicely large curve that we can do with small telescopes as well. So our educational approach, as you have seen, so we're gonna use multiple languages for sure, because we have maybe students, they are not all in Africa familiar with English or with French or in Arabic. So we try, in Africa we're diverse. So we got the north of Africa, it's more Arabic. So, and some of the regions are English speaking or other are French speaking. So we try to divide this on three parts. So we're gonna be having classrooms, online classrooms via online platform where students can learn about the activities. And also we are trying to implement some new approaches. We're gonna do individual projects or working group projects, so students can learn from each other, and especially students, they are from the same region or from the same country, so they can be in person, face to face, and they can work on this project together under the guidance of our trainer and teachers that they're gonna provide them the information that we need. And also we will be doing some individual products for people, and we can see how we can do by themselves too, because the level of student is not the same, so it varies. So we're gonna also see how this is gonna work. So the timeline for now, we are expecting to that for 1 year. So and I will tell you in a bit why, because of the funding, because we are asking also for we're seeking for funding, and we are sure that with that program and it became larger, so we can increase the engagement and interest in astronomy among students in African universities, and we can also strengthen the capacity of astronomy education through practical and hands-on experience with real astronomical data, and also establishing some online labs model that can replicate it in other regions within Africa. So for funding and resources, so it's important. So this project will be supported by my university, UM6P, which also have this vision that they are gonna help Africans and African students to do different science in the STEM, in science and education and technology. And also there is a program called called online labs between two universities, the EPFL in Switzerland and UMCSP. They have a joint program where people can ask for funding, and we have already submitted a proposal to get funding for this project, and this is not decided yet, but I think we have more chances to get this project and to work on this online lab. So we are looking for collaborators in Africa. If there is any group within Africans, universities or schools, universities, or even organization, they would like to benefit from this project, they can help us also to maintain this project. We will be happy to chat about that. And also we are looking for lecturers and trainers and people from here. This is why I would like to present this project here in the IAU, because the community, all the communities here, if they can help us by giving some lectures or even some programs, trainers, just reach out to me, and we will be more happy to chat about that and try to maintain this project within Africa. And with that, we can maybe contribute to elaborate more about and help African students to get more in astronomy and educational research. So that will be all, and I'm here to answer any questions.
Questions to Youssef? Online questions? Someone having a look? Okay. We have one.
This is great, Joseph, that you're doing all this. So question about the collaborations that have you already coordinated with universities across Africa? You were showing this map. Have you started working with them, and have you contacted their space agencies? And have you thought about doing collaboration with the space agencies, even outside Africa and the US and Europe?
Yes, I'm trying to do that, and this is one of the reasons why I came here in person to this meeting, is just to meet these people. We have a meeting with Survey Institute, and also they are helping to collaborate and making some contacts with the universities and in US and in Europe, that they can help us to and provide some trainers and even some funding to do this project. So we're also talking to our colleagues here in Africa, so how we can maintain this. I know that each country, there is someone who's like leading this activity by themselves, but I think we can go globally, because there's some other countries, they have nothing, as you see in the map. So there's nobody doing things there, but we can try to reach out to them and say, hey, there is a program that they don't need to be coming to Morocco or coming to South Africa. They can do it from their countries. And we are establishing now this program, and also we're waiting for funding. So because we need to try to build the platform and try to go to some places even to talk to people about this project. So I'm working on it.
Thank you, Joseph.
Okay. Anyone else? No? Yes, thanks, Joseph, for the talk and all the speakers of the session.
Yeah, I will make just a quick announcement. So we are going now for the poster session, which is started, and we will back here at 3:30. And this is going to be the last session. So if you would like, we're going to have a group photo here. So if you would like to join us, please feel free. So this is going to be at around 5.
She's going to talk about planetary science and exoplanets from James Webb Telescope to public outreach and education. Are you ready, Dr.
Yes,
Sumaya?
yes, yes. Thank you much.
Okay.
I shared the screen, okay?
Yes, it's all ready.
Okay. But I didn't see my presentation.
She wants to see the presentation, please.
Yes.
Can you see the presentation? Can you start?
I can't see it now. Okay.
Okay, cool. Cool. Good luck. You can start, Dr. Sumaya. She's muted.
Where is the presentation? I can't see it.
She can't see the. We have it here, but she can't see the presentation.
For me, not? Oh.
Okay, it's shared.
Okay.
Okay.
It's okay. Hello, everybody. Thank you much for the organizer and the attendee. My talk today concerning the planetary science and exoplanet from James Webb to public outreach and education. And our view, James Webb, the largest space telescope ever, have traveled a million miles into space and is 4 times further than the moon to begin its work observing star formation and the planetary systems. And exoplanet Webb is designed to answer some of the greatest or biggest questions about the cosmos. Webb pioneering mission is very stimulating and inspiring. It must be exploited in astronomy outreach and education. In this way, James Webb exploration will significantly impact the progress awareness of public, students, and kids towards the cosmos evolution on the other worlds. Very fast view about the mission of James Webb. James Webb primary mirror is equivalent to 6.5 and consists of 18 hexagonal gold-coated mirrors. The sun shield is about 21 by 14 meter, comparable to the tennis court. Its weight is approximately 13,700 pounds. Operating temperature of James Webb is about minus 370 degrees Fahrenheit, below 6 Kelvin. It attached 4 instruments with James Webb. First is a near-infrared camera, near-infrared spectrograph, and near-infrared slit spectrograph, and mid-infrared instrument. Main job of James Webb is to answer fundamental question about the universe. With 100 times more sensitivity than Hubble, we can detect infrared light generated by galaxies as they formed more than 13.5 billion years ago to seek the light from the first galaxies in the early universe. Explore our own solar system as well as nearby planets orbiting other stars, which called exoplanets. We will reveal the birth of stars and the planets and examine the exoplanets for the potential of life. With new developed technology and its benefit to the society, measuring eyes based on the development technology of James Webb, scientists improve the area of wavefront sensing technology. This led to a new wavefront optical measurement devices and spin-off. Laser interferometers which based on development technologies for James Webb, a new technology of high-speed test devices with wide range of commercial application within astronomy, aerospace, semiconductors, and the medical industries has been developed. The integrated circuit used in camera repair with investment cryogenic applications specific integrated circuits led to development of the technology that are now flying on the Hubble Space Telescope. Infrared sensors technology developed for Webb are now the universal choice for astronomical observations, both from space and the ground. This technology is also being used for earth science and the national security missions. The other worlds, where and how do planetary system form and develop. Until recently, the only planetary system we could study was our own solar system. Now, astronomers have found evidence for thousands of planets around stars other than our own sun. These are known as exoplanets because of this we are getting closer to answering key questions such as, is Earth the only planet hosted life? Do other planetary systems similar to ours exist? Are we alone in the universe? The impact of Webb on exoplanet research, building on the legacy of NASA, Hubble Space Telescope, Spitzer Space Telescope, and other ground and space-based observations, James Webb Telescope is expanding our understanding of the exoplanet's atmospheres. Why James Webb is an infrared telescope key to characterizing the atmospheres of these exoplanets. The benefit of making infrared observation is that at infrared wavelengths, that molecules in the atmosphere of exoplanets have the largest number of special features. The ultimate goal, of course, is to find planets with a similar atmosphere to that of our Earth. Webb is telling us more about the atmospheres of exoplanet, of extrasolar planet, and perhaps will even find the building blocks of the life elsewhere in the universe. Over the past 3 years, researchers have identified a wide range of exoplanets, including small rocky and giant gas planet. Again, with James Webb, a wide variety of exoplanets have been successfully observed. The illustration shows that the new exoplanet range from very small rocket to very giant gas planets. How many exoplanets have been discovered? As of 25 July 2024, there are 5,741 confirmed exoplanets in 4,285 planetary systems, with about 960 systems having more than one planet. Greater than 12,000 are candidate exoplanets and are subject for further observation and study. The past and the present and the future exoplanet mission, Korot, which launched in 2006, the convection, rotation, and the planetary transit mission. Then Kepler in 2009 was an exoplanet discovery machine, accounting around the 3/4 of all exoplanets discovered so far. The NASA successor, TESS, a transiting exoplanet survey satellite, and the NASA ESA Hubble Space Telescope, and the NASA Space Mission. NASA ESA Canadian Space Agency James Webb Telescope continues the legacy of exoplanet research by mission not designed solely for it. ISA GA mission telescope, also one of the observed space mission telescope for exoplanet. The characterizing exoplanet satellite KIPUS was launched in 2019. The next upcoming mission is Plateau, the planetary transit and oscillation of star mission, planned to launch in 2026. Ariel, the atmospheric remote sensing infrared exoplanet large survey mission, is foreseen for launch in 2029. NASA and ESA Roman mission, which will use a technique of gravitational microlensing to find the distant galaxy. This illustration shows a past, present, and future space satellite, which main job is to observe and explore exoplanet. This statistics show that the number of exoplanet publication from 2020 to 2024 is is multiplied by 3 times, which indicates that the exoplanet research are the most interesting subject today. The habitable zone and the life on other worlds. The habitable zone is the region around the star where we can expect to find the liquid water at surface. The illustration this shows the habitable zone for the solar system, and we can see the borders of this habitable zone, and the Earth is inside this one. So we have the light, and this other illustration show the habitable zone for hot and cold and mid temperature stars. So it different as the temperature of star change. What are scientists research for? Scientists research search for to know whether planets support life or not. The scientists analyze the reflection light from the planet to see if the planet has an atmosphere or not. Then they looking for any evidence for oxygen, which indicate about maybe planet or algae component, and water, and looking for sign for biology activity like methane. James Webb brief about planetary system and exoplanet. James Webb exploring our solar system with the near-infrared camera, observe Jupiter, Saturn, Uranus, and Neptune with very detailed features, and penetrate the other condition that obscure any feature for this object. Also, with huge mirror and infrared sensitivity make it easier to see small faint bodies such as Kuiper belt object, comet, asteroid. Also with capture the dart impact. This illustration shows the near-infrared camera for Moon, Jupiter, Europe, with feature of carbon dioxide distribution on its surface. For exoplanet, James Webb could observe the exoplanet HIP 6546b in different band of infrared range, and we can see how we penetrate the dust and clouds that obscured the planet. Another example of exoplanet is illustrated here from giant gas planet, Neptune, sub-Neptune size planets, and terrestrial, rocky, and super Earth planet. This is some examples of what James Webb observed of exoplanet. Exoplanet and space exploration for astronomy education and public. Why bring exoplanet and space exploration to public and astronomy education? The goal is to breeding and develop the new generation of science appreciation, creative and innovative one. And how bring exoplanet and space exploration to public and astronomy education to appreciate scientists and share the value of science, announce about the Nobel Prize winner and the Kavli Prize winner about exoplanet and their discoveries and their investigation. It could be good way to has attention of the student and public. Share images of discoveries that increase, inspire, and curiosity. Provide the different resources of space science and make it accessible. Work with educators to develop programs and resources for students. And this will offer a good opportunity to inspire and involve young people. Help people experience the joy, beauty, and power of STEAM through various and meaningful engagement with space Webb discoveries. Increase the community events, broad the participant, including the deprived population, people who are not space or science fans, etc. With James Webb Legacy and website of NASA, we can also expose some photos and some image of James Webb to see public about the James Webb component and size. This is a very good image to imagine how James Webb is very huge, comparable to 10th court or very huge building. Also, this is the module of James Webb, which contain all its instruments launched with it. The comparison between Hubble and Webb it will be very impressive and useful for public and young people to know that Hubble has many good for 30 years, very good exploration and investigation about our universe. So if we increase the mirror and the instrument and also the orbit, it will change very much for more than expected. The comparison is good for mirror size and orbit with Hubble and Webb. Also here the instrument of Hubble comparable to that of James Webb, and the wavelength observing wavelength is of both of them. With this, this will combine with some explanation about the useful of infrared observation and so on. Also, this illustration show what we see of the pillars of creation with Hubble alone, with James Webb alone, and here the both. So we can see, or can explain that the infrared radiation will penetrate the clouds and dust of the cloud and see the stars and object behind. The Planetary Society has very good resources for exoplanet. It explains the method of exploring exoplanet with very simple way. Infographic. We can use these resources to our community and our students in school to explain about the method of exploration. Also with the network of astronomy school education, we organize the annual workshop for teacher and for student to know about many subjects in astrophysics. One of their courses is a planet and exoplanet, and it would represent it with another resource of the Office of Astronomy of Education is the astro education subject, which refer to the how you find exoplanet. So all these resources can be used to introduce the exoplanet to our community and for education and for the competition of name exoplanet or name of exoworlds with the Office of Astronomy of Outreach, which released in 2015, 2019, and 2022. It gave very good opportunity to introduce the exoplanet, the habitable zone, and all the discovery about exoplanet to the public. Also, it gives good chance to the public to choose the name of exoplanet from their culture and enter the competition. We organize this competition in our community and get good results. Many seminars about James Webb and exoplanet are presented and for public all the time before launch of James Webb and when it launched, and then after with with the first images of James Webb. Also wrote a book and translate some publication of to simplify the meaning of research for planet for kids and students. James Webb inspired kids much in Egypt and in the globe. This is the gallery, some photos from the gallery of James Webb NASA Space Telescope, which submit models of James Webb. Also, this collection of art and crafts photography highlights the Webb mission. The gallery show the information of public on Webb telescope and its mission. In conclusion, we can say that the mission of the James Webb Space Telescope represent a lot. It will reveal much about the mystery surrounding the universe. The mission of James Webb is very inspiring and helps to develop the passion toward astronomy and STEM education. One of the most exciting goals of James Webb is to study star forming region. James Webb, equipped with several sensors for wide range of infrared rays, which gives James Webb the ability to penetrate the pipes of cosmic cloud and explore the planetary system behind. Using James Webb results, it is possible to attract the interest of people to know about space discovery, as it is possible to satisfy everyone's curiosity about the solar system and the exoplanet, and have answered many questions related to how it was formed. Are there star systems similar to the solar system? What are the exoplanet and the ways to discover them? What is the habitable zone? Are there planets similar to Earth? Is there a possibility of the existence of other life in the universe? Thank you much and for your attention and for the organizers. Thank you much.
Thank you, Sumaya, for this presentation. Questions from the audience? Maybe we'll start with the people here on the floor.
Okay.
Do you have any questions? No questions? Maybe online? Is there any question online? All right, no question. So let's move. Thank you, Dr. Sumaya.
Thank
Again,
you.
a round of applause for Sumaya. Thank you.
Thank you. Bye-bye.
So let's move to James Smiley. He's going to talk about the interactions between debris disk exoplanets, a multi-wavelength view towards Beta Pig.
Yes.
Okay. Hello, everybody. Thank you to the organizers for giving me the chance to speak to you all today. I've got a lot to talk to you about, so I'm going to get going straight away. But in general, we're going to be looking at the interactions between debris disks, circumstellar material that's still maintained, that's still existing around the star when the planets have been formed and are already there. So it's a real direct way for us to look at the interaction between these two things. This is roughly what we'll be going through over the next 15 minutes. So debris disks in general, crash course. This figure was in every thesis for the last 25 years to do with star and planet formation. Basic idea is we start with our cloud at the top, that it's rotating, it's collapsing, and it leaves us with a disk orbiting around the star. Over time, this will become an optically thick, geometrically thin disk from which we expect our planets to form. And the bit I want to talk to you about today is this last one. Okay, so most of our disk material has dispersed, been accreted onto the star, or form planets within the system. And what we want to look at is what remains and what exists for a few million years afterwards. And this basically happens a bit like this. Through radial drift and dust growth, we lose a lot of the dust mass from the disk. It's now in the star, the planets, or it's been lost to the environment. Disk evolution results in dissipation of the disk. And so we end up down here at low dust masses and at low fractional luminosity, which is basically a measure between our stellar black body and the emission we have from the material itself in the SED. This is what a debris disk looks like. Okay, so on the left-hand side, we've got an image taken by Alma from Faramaz et al. In 2021. This is the famous HR 8799 system. It is host to 4 giant planets. We can see them all here. How good the video works, we can see them. This is a mashing together of loads of direct imaging over many years, about 10-year baseline, and we can see them all orbiting around really nicely. But this is the debris disk. This is what the millimeter emission looks like outside. The planets are all in here. And in debris disks, we have this really direct link between the planets that exist within the system and the material that's still there. Okay, much easier to see the interaction between them than in the slightly earlier phases or later when all of the material is completely gone. Yeah, we get that. And just in case I need to motivate you any further, that debris disks are interesting, we should remember that we are in one. Okay, lots of the people who've been talking about solar system objects today, I count you as debris disk scientists, okay? You're looking at the components of our disk. We have the Kuiper belt. We're going to be looking at some exo-Kuiper belts in other systems in just a second. And we have the Oort cloud. And this gives us a basic size scale for the material we should be expecting in debris disks, tens to hundreds of AU in a Kuiper belt, and perhaps some extra components even further out. What's the debris disk made of? We have our 2 components, dust component and a gas component. Okay, the dust looks a little bit like this. These are images that are going to come out from the ARC survey. This was a review by Sebastian Marino quite recently. Basically, what we see is rings and belts. Okay, usually only 1 or 2 that we can see quite clearly. They look a bit like this. We just saw HR 8799. The really cool thing in the last 5 or 10 years is the sensitivity and resolution we've been able to achieve with ALMA and the features that have been revealed in these debris disks that usually we probably would have only considered to be in younger protoplanetary systems. So this guy here has 2 rings, and there's even material kind of in between filtering through. It looks a lot like a protoplanetary disk. This guy's got this asymmetry. It's got this bright spot over here. That substructure is something we might want to investigate dynamically to pick apart what's going on in that system. The belts that we see generally are correlated with the luminosity of the central star. So the brighter your object, the more massive your star, the further away the belt tends to be. And this stacks up with some of the physics we know about debris disks. Okay, radiation pressure is extremely important in these environments because it's optically thin. So the small grains in particular are going to get pushed out much further. But so far, this is working as a pretty good rule of thumb. If you want to link this to the earlier stages, the belts that we see, the exokuiper belts in debris disks, exist at pretty much the same locations as protoplanetary disks do out in the disk, tens or hundreds of AU. So perhaps they are progenitors, but we see that they are much wider. So perhaps that's telling us something about how they evolve, how they spread viscously over time. Cool. The gas component, okay? Until quite recently, people thought the debris disks were completely devoid of gas, so that there wasn't anything there worth considering. Thanks a lot to observations by Alma. These were some of the first ones that were taken. This was Attila Moore in 2017. But we now know of at least 20 systems that have significant amounts of molecular gas still in them, way beyond the timescales we would expect any disk to still exist. There's now an entire ALMA large program, one of the main goals of which will be to study the gas in debris disks that we know of. So this is super exciting, and it's given this whole new kind of subfield for us all to work on and to start considering. Mainly because we want to know what's going to be the result of having all this gas still remaining in these systems, because we know planets have already formed, right? They're already there. So they're going to be accreting and taking on anything that exists within our debris disk. On the left, the top left points of a collection of protoplanetary disks, and the things in the bottom right are the debris disks. Okay, so we can see on the left-hand side, dust masses are of order kind of fractions of an Earth mass, tens of an Earth mass. And the gas, well, this is the CO here, our most abundant gaseous tracer. Again, fractions of an Earth mass, even less than the dust. So this is like really quite small quantities of material that we're able to be sensitive to. But the effect it can have is really quite significant, at least early modeling suggests so. Accreting some of this material onto a planet that's already formed might completely change the makeup of its atmosphere. It might completely change the gas to core ratio. Okay, so I would be concerned about this if I was trying to link, like many of us are trying to do, the composition of a protoplanetary disk as probed by ALMA and the composition of an atmosphere that we're detecting later down the line with JWST. Okay, because something might have happened in between that's really going to mess up that situation for us, or at least mess up understanding that situation for us. Part of the reason for that is that we're not quite sure what the nature of this gas is so far. There's two main theories, and we're making progress on the known systems that we've got. It can either be primordial gas, by which I mean it's left over from the protoplanetary disk stage. Okay, so it's going to look a lot like what we see from the MAP survey and from work that's gone into the earlier stages of circumstellar disk. It's very hard to maintain gas for that long. It seems sort of counterintuitive, but there's been some really good work by Nakatami et al., who are looking into perhaps A-type stars in particular are a perfect ground for gas in systems to survive for a very long time. Or it could be secondary gas, which we presume to be released during collisions from these exokuiper belts we've been seeing, all right, where the grains have grown very large. We've got pebbles, we've got planetesimals of sort of up to kilometers inside. Big destructive collisions of those, heats things up, throws out all your volatiles that were locked in at previous stages, probably early in your protoplanetary disk. The composition of this gas is going to be completely different to that of the primordial gas, okay? It's not going to have anywhere near as much hydrogen, because hydrogen can't freeze out in the disk. What might this do to our planets, okay? What might this do to anything that's accreting it? How might that muddy our linking of the compositions? Precisely. So we're going to look at this in one particular system, in Beta Pictoris, which is a very well studied, very well known object. It's been observed with virtually every major facility. And it's a really good test bed for our debris disk physics because we've characterized it fairly well. Intermediate mass star, it's only 19.4 parsecs away, which is why we like to try and observe it. We can usually get much brighter signals than in other systems. And it's got two planets in it, okay? This is the one that's been seen via direct imaging, Beta Pic B. We've got an edge-on disk, which we're going to see in just a bit, so it's moving along the plane like so. From radial velocity data, we think we've also got a Beta Pic C, both of which are very massive planets, 11 Jupiter masses and about 8 to 9 Jupiter masses, respectively, at around 8 and 2 to 3 AU. So everything we're about to see, all these images, bear in mind, we've got two massive planets orbiting, stirring things up, influencing our system. Next one. Before we get into the ALMA stuff, here's some previous work that's happened at shorter wavelengths, and there's some key substructures I want to point out. In particular here, we have, this is HST data, we have a warp, a famous warp between or within 100 AU. You can see the outer disk is fairly well aligned, and then we get this wiggle in the center. Also, on the right-hand side from VLT and Vizier infrared wavelengths, this was Scaffer et al. In 2023. We get these clumps, okay? When you remove the principal component, which is a very bright emission, very close to the star, very small hot dust, they revealed this clumpy nature behind, and this is important. We're going to come back to this a lot. There's a big clump in the southwest corner of the disk, okay? It's been repeatedly seen at infrared wavelengths and at shorter wavelengths than our ALMA frequencies. And it's difficult for us to understand, basically. So these are two key features I want you to remember: a warp and a clump. Cool. Now we're going to look at ALMA. The key thing about ALMA is that we're looking at very large grains, relatively large grains, okay? Millimeter, centimeter sized particles. They're probably decoupled from any gas at earlier stages when there is more material in a protoplanetary disk. Here, they reside in these belts, and they indicate where the dust has accumulated and sort of remained. Also, we're seeing this key molecular tracer, carbon monoxide. And we've got multiple frequencies and indeed many different ALMA configurations. So the different bits of information we've got are really adding up to give us something powerful. So these are two new images we've got. This was only a couple, well, last year, band 3 observations of Beta Pictoris were basically edge on. So you're going to get this long cigar-like shape. This is in the millimeter continuum. You see a bit of a clump on this side, some emission at the stellar position, less so over here. But the really striking thing is in the gas, okay? We've got this super bright clump right where that southwest clump was in the infrared. Notice how it's not that obvious in the dust here at ALMA wavelengths, but it is in the gas, and a much fainter disk on the other side. So this is cool, but the real power comes in combining this with the other observations we've got and doing a multi-wavelength study, because then we can learn a bit more about the dust and the gas. So this is our full gallery of dust images that we now have from ALMA of Beta Pictoris. I gave them all a color each just for fun. But this is what we want to do with them. So we can calculate a spectral index, and this can tell us about the composition of the dust, what's it made of, what's it doing there. You can do this for a disk averaging over the entire disk, and we've been able to compare lots of different debris disks in the past by doing this. Note that Beta Pictoris has a rather large size distribution index, consistent with a collisional cascade. So that's kind of confirming to us that there are some very strong destructive collisions going on in there. I had all these lovely spatially resolved observations of the disk, so I tried to do this as a function of position in the disk, and I must be honest, I was expecting a bit more of a signature over at the clump over here, but it didn't quite turn out. This is relatively flat, right? We can see here there is something of a rise from the northeast to the southwest side of the disk, but it's not that stark. Maybe because we're looking through the edge of the disk and it's not really giving us a radial profile. Perhaps because our clump in terms of millimeter dust is not that different from the rest of the disk, okay? We don't see it as brightly as we did in the infrared and the gas. Perhaps that's backing that up. The other cool thing we could do is look at the composition of the gas. From early indications, the gas from our modeling seems to be in the hotter and the less dense, sorry, all the way around, less hot, more dense end of our modeling. And so that can tell us about something that we are accreting onto any planets within the system. The two families of ideas trying to explain this clump are that we've got a massive collision, a giant impact that over time will create this sort of circular secondary disk, and the other is resonant trapping between any planets that may be in the system. Okay, I'm beginning to run out of time. We can check some of these theories by looking at the extension in the clump, for example. Initially, it looked like we did have some extension, but when you use the spectral resolution of the data, you can see actually perhaps not. Maybe we are more consistent with resonant trapping or a single giant impact. One final thing I want to show you is that consistently in every single epoch we've taken data, the continuum is pretty much flat. The CO is slightly inclined. Okay, so remember that warp we had earlier in the HST data? We've now got all sorts of misalignments, okay? The planet itself is on an inclination of about 0.7 degrees. The molecular gas every single time was 3 degrees off. The warp was 4 degrees off, okay? That looks like a really interesting problem for any dynamical modelers who could perhaps do something to what we see, similar to what we see in protoplanetary disks, where a planet on a misaligned orbit can sort of tear or break that distribution, causing a warp, okay? And it ends up looking a bit like that. Finally, very, very finally, here is an image from JWST. This was Reboido et al. Just this year. The most weird thing about this is this feature on the end, which they call the cat's tail. It's still not entirely clear how this came to be, but it matches up almost exactly with the edge of our gas disk and is launched from the very outer edge of our clump. So that is something for us to investigate in the future. And I'm going to leave it there. Sorry. Thank you very much.
So I'm taking questions from the audience. Is there any question? Okay. Please introduce yourself for the online people.
Sure. Lynn Hillenbrand from Caltech in the US.
Cool.
You mentioned the possibility of accreting gas onto planets. What mechanism are you envisioning? Is that just Bondi Hoyle or something else you're thinking of?
Yeah, something like that. So this was a paper by Quentin Krau in 2020. And yes, if we've got a planet sort of just inside of where our belt is of the gas and the stuff, they were starting to look at fairly initial investigations as to how that material might go in. So there's major dependencies on, for example, the height of your disk relative to the size of the planet, how you're going to funnel material onto that. And we haven't got anywhere near as close to characterizing that as they do at protoplanetary disk stages. But yeah, from some assumptions of how much material through the accretion rate of the disk is actually ending up on the planet, they started doing calculations as to what this meant for core to gas ratio and composition. And yeah.
Okay, I thought you were discussing the debris disk being reaccreted.
No, so sorry. So the material from the disk onto the planet itself, feeding onto the disk would solve us a lot of problems as to why this material is still there. The red light's flashing at me, so I'm going to stop. But yeah, thank you.
So another round of applause for James. Thank you. That was good. So I'm calling Suzanne Falzner. Sorry if I mispronounced. She's going to talk about connecting disk lifetime variety to planet diversity.
Hello, good afternoon. Okay, better? Yeah, okay. So what I want to talk about is connecting disk lifetimes to planetary diversity. And you might think disk lifetimes, that's what we are long through, right? But perhaps not. Okay, let me remind you how one determines a disk lifetime. So one looks at star clusters because there are many stars of a similar age in a relatively small area. And then one looks for disk indicators that can be infrared access or accretion signatures. And then you determine the relative number of stars with this indicator and say this is a disk, and repeat this for clusters of different ages. And this is a typical picture where the violet symbols are the measurements from Heisch, who introduced this method in 2001. And because he had only six clusters, then he put a line through it and said, by 6 megayears, all stars have lost their disks. You might notice this little point right in the right corner at the bottom. This is one he excluded and said, oh, there we have 3% disk fraction. That's probably a debris disk. At that time, he couldn't do better. So these black points you see are measurements which are more recent. And usually people put a exponential through it. And if you go at 50%, you end up somewhere between 1 and 3, depending what your sample of clusters is. And the conclusion that people draw from it, that most disks are dissipated within 1 to 3 megayears, putting a lot of pressure on planet formation models, because planets have to form fast, especially the gas giants, in less than 3 megayears. So this has been a lot of pressure on anybody who does planet formation models. In 2022, Michel et al. Had a paper out where they looked only at co-moving groups. They're relatively near. They're usually within 200 parsec. And what they found is that the disk lifetime in co-moving groups is longer. Their conclusion was that these are very sparse systems, and that this is an effect of density, that in the other ones, the density of the cluster gives some additional process. So I've been doing 20 years this kind of simulations, and I thought, yes, there's a difference, but this difference is really, really big. Okay, bigger than I would have expected. And then I did something really odd. I thought, okay, if that has to do something with the clusters, let's plot it as a function of the distance of the cluster. And I got something really weird out. And that is that the disk lifetime, so I had clusters that are within 200 parsecs, between 200 and 500, and you see it. So made distance bins, basically, and gave that different colors. And what you see is basically the more distant the clusters are, the shorter is the disk lifetime. Really, really weird. Okay, the disk lifetime shouldn't be a function of distance of the cluster. So, but distance roughly translate into limiting magnitude. So what actually happens when you go further distant, you see more and more only the high mass stars in it. And it's known since quite some time, but not really discussed normally, that the disk lifetime is a strong function actually of what stars you are looking at. So I looked for disk fractions given in a cluster of different stellar masses. And when you look at it, it's actually Apascopio and UCL LLC are the most reliable data, because here I've given the size of the sample. So they have, one has 1,700 and the other's 2,300 stars. So if you determine a disk fraction in that, this is really certain. You have a relatively small error, whereas some of the other clusters have just 50 stars in them. So a disk fraction there has a large error. So I base now the rest on that. And for those, you have it as well in dependence of the stellar mass. So you can do that and put a line through it and, you know, get the disk lifetime, the disk fraction as cluster H based on these 2 points for different masses. And it depends a bit on what you assume as initial disk fraction, whether you assume that every star is initially surrounded by a disk or whether it's 80%. So you get that basically dependent on that. And that translates into this plot here, where the median disk lifetime is shown as a function of stellar mass or what type of star you have. And the disk lifetime decreases for higher mass stars. And what is really important here, most stars, we had that in other talks, is M stars. So most stars have a disk lifetime somewhere between 5 and 10 megayears. And the 1 to 3 megayears that we usually count is for the high mass stars. This has a huge influence on how we perform our planet formation models. I must say the transition is not well determined yet, because for the high mass stars, there is a low statistics. So I've plotted here 3 lines. This could be, any of those could be reality where it goes down, but it goes deeply down at some point. Okay, I want to as well caution a bit the term of a mean disk lifetime, because the last 10 years, a lot of relatively old stars have been surrounded by disks. And I just want to show the most famous examples. If you look at HL tau and if you look at TV Hydrae, and this is a bit superficial, this statement, then they look very similar, but they have very different ages. One is 3 megayears old and the other one is 8 megayears old. And in addition to that, an increasing number of Peter Pan, so-called Peter Pan disks have been found, which are 20, 30, 40, 50 megayears old and are still protoplanetary disks and not debris disks like we heard in the previous talk. This means that the individual disks seem to develop on very different timelines. So what we try to do is convert that, the disk fraction as function of cluster age. You can convert with very simple mathematics into a distribution of the disk lifetime. And we did that, so with only 2 points, taking Upper Scorpio and UCL LLC, and as well taking the others into account, and the difference is not very much. So we get that out basically and did a lot of different distributions. And what we find is that a Weibull distribution best describes actually this distribution. But the type of distribution is perhaps not the most important thing. The really important thing is that you have a really big width for all of these distributions. So you have typically a 5 mega year half width of these distributions, which is enormous. So talking of a mean disk lifetime is, it doesn't say much. So you can do the same game for different stellar masses, and you see the distributions for these stellar masses. And now I want to make the link to the planetary systems. So when you look at low mass stars and high mass stars and look at the type of planets that they are surrounded by, you get something like that. The color here indicates the stellar mass. So blue is low stellar mass and red is high stellar mass. And you look at the radius of the planets, and you can see if you look just at the high mass stars, you get much bigger planets than you get around the low mass stars. And this is just a very simple illustration of that, and people have been looking at that much more in detail than I've done here. And they found, for example, Howard and Sabota in 2012 and 2021, that high mass stars are more likely to form high mass planets than low mass stars. On the other hand, low mass stars form many small planets. And what's perhaps the most surprising thing is that they form disproportionately high planets with a high heavy element content. So it seems that when you have a high mass stars, you have a relatively short-lived disk. In this short time, it forms a high mass planet. Whereas the low mass stars have loads of time and they can build up one planet after the other, or have loads of time to do it slowly. So in total, it's actually the low mass stars are much more efficient in converting the mass that they have in their disks into planetary material. So it seems actually that this long disk lifetimes are actually beneficial for planet formation. And that's it. Disk lifetimes of most stars, which is the low mass stars, is 5 to 10 mega years. So the constraints on planet formation theory are much more relaxed. Only high mass stars have these short disk lifetimes of 2 to 4 mega years. But this is a tricky one because you have to build the gas giants in a really short time, right? Disk lifetime distributions are generally very broad. So if you look at one system, you can't really generalize that to others. Longer disk lifetimes allow low mass stars to produce many low mass planets. And planet formation models, they don't have to rush anymore, right, to get it really fast, but they have to take the disk lifetime dependence on the stellar mass into account, and they have to explain the spread in disk lifetimes, which I think at the moment they don't do. Thank you.
I was wondering if you could talk about your preferred age scale or method of determining stellar ages. I know I used to think a lot about this problem as well, and it's quite challenging to get the ages right between 1 and 10 million years. So what is your method for doing that?
I'm not actually doing any method. I'm a theoretician, so this might be a bit surprising. So what I did, I basically looked at all the data that are available. So in total, I think it was 70 different clusters. And of course, there is a wide spread and people do different methods. But overall, you know, having so many in it and, you know, taking as well that some do it this way, some do it that way. Overall, this comes out. So I hope that the, you know, different methods level out against each other. But this is, I mean, the shocking thing was when I did this with the distance, because that's the thing which should not have happened, basically.
Hi, Dominique T, University of Geneva. I was just wondering, you said these long-lived disks are more efficient at making planets. Is there a chance that the presence of planet is somehow keeping these disks going longer than they might otherwise?
Yeah, I mean, the question why this is, why do they live so long, I think is actually, and why are there so different ones? You know, if you look at the distribution, there are ones which end their life if you look at the low mass stars at 1 mega year, and you have ones that live 20 easily. So I have no solution for that, right? There might be a combination of many different effects. For example, the short-lived ones, perhaps they are mostly in binaries. Perhaps they are cut off by flybys, or there is a photo aberration. This has to be all checked, but it could as well be, for example, yesterday there was a talk about that the spins of these disks are differently. That probably says something. So I've presented here this one distribution, but it could be as well an overlap of two. This is what I was thinking yesterday. So.
Thank you.
Maybe one last question. Nothing? Cool. Another round of applause for Suzanne. So now I'm calling Ms. Tamara Malyarova, talking about volatiles and CO ratios as a result of dust drifting in self-gravitating protoplanetary disk.
Hello, everyone. I need to try moving with this thing. Yeah. I'm going to talk about CO ratios in protoplanetary disks and how can they help us to constrain planet formation mechanisms. So the topic of CO ratios has been already discussed in this session. For example, today in the morning, there were a couple of talks about that, and I won't concentrate too much on it. But the idea is that carbon and oxygen contained in the molecules in protoplanetary disks can be redistributed between gas and ice phases due to sublimation and freeze out of the volatiles. This idea was very popular since the paper by Ubach et al. 2011, and it is CO ratio thus is thought to be a good proxy of planet formation, because we could compare the CO ratios found in exoplanetary atmospheres with the CO ratios in protoplanetary disks, and thus constrain the material the planets could form from. Would it be the gas or ice phase, or the location of planet formation? Even without the comparing with the models, there is already a lot of observational data. For example, in this work by Hawk et al. 2023, they looked at the CO ratios in the Jupiter-like massive planets and found that there is a discrepancy between CO ratios of transiting exoplanets and directly imaged exoplanets. Here you can see a plot from this work where directly imaged exoplanets have a very narrow range of CO ratios, while the transiting ones have a very wide range. So they suggest that maybe those kind of planets are formed in different mechanisms. And this is what we are going to explore using the modeling. The model we use is Feosat code. It was already introduced in the morning session by Anastasia Topcheva, so I will only briefly recall the features of this model. This is a 2D model, thin disk approximation with dust evolution and hydrodynamics, of course. It includes dust drift and also a very important feature, it includes the volatiles and their evolution. So these are the 4 molecules we're considering, and we start with some abundances from protostellar cores, and then we evolve it for 500,000 years. The feature I'm concentrating on is the volatiles, and the volatiles in the model can be, the distribution of volatiles can change in several different ways. First of all, they can be sublimated or frozen out from onto dust populations, so we can have snow lines there. Also, the volatiles can be transported throughout the disk. The gas phase molecules move with the gas, ice phase molecules move with the dust, and ground grains can move relative to the gas, while small grains are frozen into the gas and move according to it. And the third way that volatiles can be redistributed over the disk is the dust growth, because dust can collide and grow in size, and ice mantles also are redistributed between the dust populations as dust can grow. Another important feature is the feedback from ice mantles onto the dust evolution. We have different fragmentation velocities depending on the presence of ice mantles, and this creates changes in dust distributions. So what we are doing here is we run the model, calculate the distribution of the species, calculate CTO ratios from that, and compare it with the initial value, which is 0.34 in this model. And after that, we will look at the CTO ratios and try to figure out what it means for planet formation mechanisms. So this is how the results look like. These are snapshots from the model at different time instances, and these are gas and dust parameters here. And what we are interested in is that there are different features, such as spirals at the early stages, or even clumps formed in self-gravitating disk. Then we have also rings in both dust and gas. And we also have features associated with volatiles. The dotted line here is the water snow line, and there is a sharp change in all the parameters at the snow line in all time instances that are caused by this feedback through fragmentation velocity. So there is a variety of dust and gas features, and they are connected, motivated by the presence of volatiles. But the volatiles are also affected by the gas and dust structure. So I won't concentrate on this figure too much, but these are the radial distributions of some molecules here and of the main gas and dust parameters. We are interested here in temperature, shown in red lines in the upper plots. If in early disk moments the temperature distribution is monotonous, then later when the dust structures form, there are some structure in temperature distribution. It can be inverted, and which means that in some disk regions, we can have multiple snow lines of some volatiles. So here you see there is a cold ring inside the main water snow line where water can be frozen again. So we have multiple snow lines of H2O, and also at larger distances, multiple snow lines of CO2. For other volatiles, more volatile molecules, we don't have such features. They have only one snow line in the disk, but they also have these features like accumulation of the volatiles at the snow line caused by dust drift. Dust drift creates those bumps at every snow line, but it also creates overabundance of water and CO2 in the inner disk, because grains bring all those volatiles from the outer disk regions to the inner disk. And then when they sublimate, the gas phase stays there and the volatiles accumulate. So the inner disk is enriched in these volatiles. And let us look finally at the CTO ratio. So here is the plot of distribution of CTO ratio in the gas phase, the red line, and in the ice, the blue line. What we can see here is that, of course, there are sharp changes at the snow lines that are present in the simplest model. but also we have multiple snow lines, so the structure is more complicated here. And also we have accumulation of volatiles at the snow lines. That's why we can have bumps such as this one at the methane snow line, and also the bumps in the ice phase CTO ratio at the snow lines, because the icy molecules also accumulate there. Another interesting feature is the variation in the total CTO ratio that is seen in the black line between the snow lines of CO2 and CH4. The composition of gas and dust doesn't change there, but what changes is the ratio between dust and gas. So, for example, here we can see dust to gas mass ratio and total CTO ratio, and we can see they are anti-correlated. That's because when we have a dust ring, most of the carbon and oxygen are in the ice phase. There is a lot of ice. That's why total CTO ratio is determined by the ice phase. And when in between the dust rings, it's mostly gas that contributes. So one of the features I want to stress out is the anti-correlation between the total CTO ratio and the dust to gas ratio in the disk. Another feature is the distribution of CTO ratios itself. So here is the evolution of CTO ratios with time. This slide shows the radial distributions of the vertical axis and how it changes with time. We see that in the beginning, CTO ratio in total is the same everywhere in the disk, but then when dust starts to drift, it changes, and mostly because oxygen-rich volatiles move inwards, we have oxygen-rich inner regions and carbon-rich outer regions. We also have the higher CTO ratios around the snow lines in both gas and ice, which I already mentioned. And in general, CTO ratio in the gas is higher and CTO ratio in the ice is lower. What can it tell us about the planet formation? So we have those structures of the disk, and we can look at the disk regions where planet formation is possible. We consider two main mechanisms triggering the planet formation. First one is gravitational instability. We can find the regions where atomic Q parameter is less than 1 and assume that these are the regions where the matter can be gravitationally unstable enough to form a planet. And these are the regions shown in these blue regions in the disk. It is mostly earlier moments before 250,000 years, and they are distant regions beyond 10 AU. So it is early stages far away from the star. Another triggering mechanism is streaming instability that creates planetesimals from pebbles. And we use the criteria of streaming instability to determine the regions where it could be triggered in our model. So we find that this is mostly the inner regions inside dust rings at later stages of disk evolution. So these are the regions where planetesimals could form, and then later they could form planetary cores and planets. So we have those regions into mechanisms, and then we can compare CTO ratios in these regions and see if they are different. And this picture is the distribution of CTO ratios in these two mechanisms. This blue line here is the CTO ratios in the regions that are subject to gravitational instability. And we consider total CTO ratio here because gravitational instability involves both gas and ice. And we see that the distribution is quite narrow, around 0.5. And it is fairly consistent with the CTO ratios found in the atmospheres of directly imaged exoplanets shown in these black dots. At the same time, if we calculate CTO ratios for streaming instability regions, we should look at the ice phase CTO ratios that are shown in the yellow line here. Mostly, the ice phase CTO ratio is close to 0 because there are many planetesimals, many pebbles planetesimals consisting of water, but they can be as high as can have as high as 0.5 CTO ratio. But with the streaming instability, it is and not direct connection with the exoplanetary atmospheres, because we need to make planets from these planetesimals. And this is where variety can begin, because in these regions, if we form a planetary core, it would create both gas and ice in different proportions. So if this planetary core is assembled in a by streaming instability, if it creates more gas, it will have higher C2 ratio. This is the range of C2 ratios shown by a red line in the regions with streaming instability. So here we can conclude that if a planet travels through the disk and collects a lot of material, it can have any C2 ratio in this wide range. Which is what probably happened to transiting to exoplanets that are mostly hot Jupiters, and they must have migrated to their current location throughout the disk. So this is what I wanted to tell you. So the main things I want to show is that there is this anti-correlation between dust-to-gas ratio and C2 ratio in total, and that the C2 ratios of planets formed by gravitational instability in the model consistent with the C2 ratios observed in directly imaged exoplanets. And transiting exoplanets should have migrated through a variety of these conditions. Thank you so much.
Thank you, Tamara. I'm Jamila from Liège University and Qadaya University, Morocco. My question, we know all that C2 ratio is great diagnostic for planetary formation, but like hot Jupiters that have an extended gas envelope, we know that super Earths often possess a thin atmosphere with that represents only a small fraction of their total mass. So given the relatively small gas of super Earths, how much can the C2 ratio of their atmosphere tell us about where they formed in the disk?
Yeah, that's a tricky question, because you need a lot of modeling to actually connect the formation mechanism with the current atmospheres, because there is also stratification within the planet. There are also some other processes like outgassing, if it's primary atmosphere or secondary. So this needs to be considered within particular models concentrated on the planet formation itself. So what I'm looking at is the disk, just the initial conditions for planet formation. So maybe we cannot say anything about these terrestrial planets.
So, okay, are you interested more in the C2 ratio of the atmospheres or the C2 ratio of the whole planet?
Of course, that would be the C2 ratio of the whole planet, but probably in some cases it is the atmospheric C2 ratio is representative of the whole C2 ratio, which is not guaranteed, of course, but what we have, we can use.
Can I know how do you estimate the C2 ratio of the back composition of the planet?
I don't know. I don't.
Okay. Another question about the pebble drifts. So,
yeah,
how might the C2 ratio differ if the planets form through pebble drift or migration?
I'm sorry, I don't understand the question.
I mean that the C2 ratio, how can, okay, let me explain another way. So through the pebble, if the planets form through the pebble drifts or through the migration, how can this process alter the C2 ratio of the planet?
Yeah, I think the C2 ratio of the planet would depend on which regions the planet crosses during its formation stage and when it happens. Like if it happens in the early disk, the C2 ratios are probably not that diverse. When it happens later, it could create high C2 ratio or low C2 ratios depending on the region. So I think the dedicated modeling is required. We don't really have planets here. We just only have a disk.
Okay, great. Thank you.
Thank you. Another round of applause for Tamara. So the next talk will be presented by Hilo Panoptis. Am I pronouncing? Oh. Yeah. Okay. So she's going to talk about team empowering communities, Project Panoptis, and the wisdom of enhancing the power of wisdom. Thank you.
Just press the button. Which one?
Yeah. So this is to go next.
Okay.
This is
Back.
previous,
Okay.
and this is if you need the.
Oh yeah, fantastic. All right.
Attention to the lights. If it's
Oh,
over,
yeah,
so
perfect.
the next question.
Yeah, the next session. Okay, I'm going to. Okay, I can't walk around. All right, this is more about outreach. We're located in Hawaii, and we live and work right under the telescopes in Hawaii. We have a new outreach model, and our goal is to reach out to indigenous and hard to reach and underserved areas of the world. Of course, in Hawaii, we have islands, we have Micronesia a bit further, and we're trying to bring, oh, thank you so much, sir. We're trying to bring research to local areas so students can have research projects to do in their bachelor's degrees and masters and PhDs and so forth, and to actually alleviate brain drain. So let me look at this. The next slide. What we're known about, our organization was founded in Hawaii because we wanted to take citizen science from the telescope, from people at the telescopes there, and bring them to indigenous areas and underserved areas. And we've been bringing Project Panoptes to areas of the world where they have no access to science. And Project Panoptes is sponsored by Breakthrough Initiatives. They want to bring 1,000 units to Africa eventually in the next few years. And Project Panoptes, for example, is a perfect example of our data collecting instruments that we're trying to bring to students worldwide where they can't have a lot of resources. And Project Panoptes does exoplanet research. It collects real data. It looks for slow transit planets, so planets that take a few years to pass in front of their stars, and so much smaller planets. It occupies a niche in the world, which is unusual because most of the programs look for very rapid transits. So our operational approach is to bring outreach data collecting instruments to students for outreach programs that last 5 to 10 years and can be replicable by the students locally. So they can use a project and teach the project again to other areas in their regions. Those projects also involve community support. And the other thing is that we teach students to take leadership roles. So we teach them how to go out in their communities and talk to the local businesses, the Chamber of Commerce, and their political body, the political body of their communities, and reach out to politicians and so forth to push for or to instigate STEM-centric economies. So we teach them to really take a leadership role and bring in the community and the political body. So this is our model here. You don't have to read it. It's way too small. But at the center of our model, we have data collecting instruments. So Project Panoptes right here that you see right there is one of the examples, but we also bring radio telescope, muon detectors, neutron detectors. We bring other projects. Right now, we have one that we have in sight where we will push or ask students worldwide and in indigenous areas to collect plants for terraforming. So in Hawaii, we have a few agencies looking at collecting better plants to plant on Mars. They're part of the NASA program. And we're looking for better crops for the moon and so forth, and for Mars in the future. So all these programs are always led by students. The model also has a support system for schools to create curriculums and to teach, to help students with becoming mentors and teachers in their communities. Also, so this is another also component of the program. We have outreach programs. We teach them how to do outreach and so forth. And the most important part in my mind is that we have a lot of very smart students out there that study that are amazing in their fields, but oftentimes they're not business savvy, they're not leadership savvy, they don't know how to go about in building their infrastructure around themselves to a bigger level. So we teach them leadership. And at the end of the day, we also offer worldwide collaborative toolkits so they can access any organizations in the world. They can reach out to mentorships on another continents. They can become part of other projects and so forth. And so basically, what is the goal with that? We have two goals: to enrich indigenous areas with more studies where students can calibrate and those instruments to collect data, and at the end of the day, to publish data, to publish their findings, publish papers, and for students to become mentors and leaders and teach and elaborate those programs to a bigger level or to a more advanced level, or to develop new prototypes that are more advanced. And for them to also at the end to go from where they are to come to the stronger economies, to come to America and Europe and teach the programs or the projects to students in more advanced economies. So we would like the students from emerging economies to become the teachers. So I talked about the projects, the different instrument options, astrobiology, radio telescopes. We have one from the Observatory of Paris that looks for meteorites. We have Project Panoptes. I'll skip this slide. Of course, I've talked about Project Panoptes before. This one can be built by students, and they learn a lot of skills, programming, engineering, and so forth. And so I've talked about the goals. And at the end of the day, again, we want students to take ownership of those programs, and we want communities to take ownerships of those programs. We want them to instigate the dialogue with economies and businesses to see how we can develop the economy through STEM. And I was talking with, I had a little meeting this morning, and I wanted to give you an example. 30 years ago, I went to Ireland, and Ireland was one of the poorest countries then. And I just went back a month ago, and they decided to build a STEM-centric, tech-centric economy. And now, after this, Ireland is basically one of the Silicon Valley of Europe, and they've developed an economy that's strong. And I think that many countries and many remote areas can do the same thing, can become the Ireland of the future. So if also being from Hawaii, we're bringing citizen science or data collecting instruments from those areas to other areas of the world. If you have a good citizen science project that does data collecting and that does that does a lot of that students can use to build their research and also publish their research, please reach out to us, because we would love to bring those projects to our areas, to Hawaii and the United States. So that's it for today. I think if you have any questions, please ask them. And again, it was not scientific, but I think it's important to bring science to those remote areas. I think it's time to do that. All right.
All right, thank you. What you're doing is so inspiring. Thank you for your presentation. Can I take any questions from here? Or online, maybe? Nothing? Great. So applause for Anne. That was great. Maybe the mic, yeah. Jamila here was very sick yesterday, so she couldn't present her talk. So she's feeling better, thank God. So she's going to highlight a little bit of what she's doing. So she's going to talk about surface pressure impacts on nitrogen-dominated USP super Earth atmospheres.
The next, okay. Thank you. Well, I was supposed to present yesterday, but due to some health issues, I was unable to attend. So let me thank the organizer for giving me this second opportunity to present my work. So yeah, I will be a little bit quick. So in this presentation, so we will shift through into the exoplanets again. So to start, I'd like to talk a little bit about hot rocky exoplanets in ultra-short period orbits. So these planets are special class of hot rocky exoplanets with an orbital period shorter than a day and radius smaller than 2 times the Earth's radius. The number of these planets is growing grace to the test missions. So far we have like more than 70 exoplanets that have been discovered with this mission. And the observations of these planets suggest that they are tidally locked and are extremely hot on their day side, which make them a good target for atmospheric or for thermal observation with the James Webb Space Telescope. So in this work, we selected 3 different planets, 3 USP rocky planets, representing hot, cool, and warm environments. And so we compared their masses and radii with the models from Zhang, so as shown here. And, sorry. So as you can see here, so these planets are consistent with Earth-like and rocky composition, suggesting that they might have a heavier atmosphere, such as a nitrogen-dominated atmosphere. So the main objectives of this work were to explore how various surface pressure affects the thermal profiles of nitrogen-dominated atmospheres, to compare the day-sides emission spectra of these planets, both in and out of equilibrium and under different surface pressure scenarios, and in order to determine if there are indicator molecules of the presence of these equilibrium processes in this atmosphere. And finally, to explore the observability of differences due to disequilibrium and equilibrium with different James Webb instruments. So I'm going to skip this because I don't have time to talk about all of that. So here, we performed a case study comparing the emission spectra both in and out of equilibrium and under different surface pressures. And so to do, we ran 2 different models. So a thermochemical equilibrium model and disequilibrium model, where we included the effects of photochemistry and transport-induced quenching. So I show here just the resulting emission spectra for our cool planet, with an equilibrium temperature of about 600 Kelvin. So we can see that here for the 1 bar and the 0.1 bar surface pressure scenarios, the models are primarily affected by the HCN features. But for the 10 surface bar scenario, we can see that the model is determined or dominated by methane. So I will skip this too. Okay, so here we investigated the feasibility of the James Webb Space Telescope to detect whether the differences between the emission spectra in and out of equilibrium can be detectable with the James Webb Space Telescope. And so to do, we used the James Webb Noise Simulator Pandixo developed by Batalha to simulate secondary eclipses of our targets. And so this is a synthetic, this is, okay, so this is synthetic observations for our cool planet. So here with both NIRS-Peak and MARY instruments. So our estimates here show that the effects of chemical disequilibrium would require 5 eclipses or 5 observed eclipses using NIRS-Peak and MARY instruments around the HCN features to be detected with the James Webb Space Telescope. And so for the 10 bar surface pressure, the divergence caused by the contribution from ethylene and carbon monoxide would require 20 eclipses to be detected. And so our models also indicate that detecting HCN features in cooler planets can help us identify low surface scenarios with the James Webb Space Telescope. So I will wrap up with the key takeaways from our study. So we found that HCN, methane, and ethylene are sensitive to different surface pressures and various disequilibrium processes. We also found that the disequilibrium processes can be distinguished by observing these molecules in cool and warm USP rocky planets. Also, the observations of these species can be used to differentiate between the different surface lavas in such atmospheres, and so providing clues about the thickness of their atmospheres. And finally, we find that NIRS-peak and mirror instruments are more viable for the purpose of distinguishing disequilibrium from equilibrium via eclipse spectroscopy on cooler planets and warmer planets. So yeah, I tried to be quick.
Any questions here for Jamila? No? Online? Nothing? Okay, so thank you, Jamila. Another round of applause. I'm giving the mic to Yusuf for some closing remarks.
Thank you very much, Miriam, and thank you to all our chairs for chairing the session. So I would just like, yes, thank you. So thank you all the speakers and the presenters for the symposium that to make it success. But there was a lot of work behind that to organize the symposium, and I would like to invite the subcommittee to come to the stage to give them a big applause. So Zuhair, Andy, HCR is here. So we have Antonella, we have Dennis, I think he left. So we got ATR, we got Richard, we got Stephanie, we got Mariev, and we got Chian. I think she's somewhere here. No? Yeah, come please. And we got also Aline. So please give them a big applause for reviewing more than 100 abstracts for the symposium. So, and we can take a picture together, and after that, we will have a picture for all the participants in the symposium. So, I would like also to thank the local organizing committee, especially Abdul Karim and other colleagues for working on the website and doing all the some local organization here. So talking to some speakers and organizing the materials. So thank you very much to all of them. I will extend a special thanks to our invited speakers for making it here, most of them to the South Africa, to talk about the research and highlighting their contribution. So I would like to thank especially Mark Clampin from NASA, Nicole Collin, Jianji, Light Fletcher, so Bing Yang coming from Chile, Jernomo Villanova, our colleague Maram Kerry from Senegal, Marie from Canada, and our colleague Sumaya Saad from Egypt. So thank you all, and are you all invited to take a group picture for the symposium. And please, for those who are online, please, I will stop sharing. You can turn on your camera if you want to be in part of the picture. So can you bring please the Zoom here for the online people? Thank you. No, everybody, not only me. No, I want people on Zoom. Yes. Yeah, a gallery view. Yes, I don't know why. Yes, great. We saw you all. Take a picture. So always following the rules. So the taller people down, the shorter people in front, sorry. I will be sharing these photos on a Drive folder and sharing it with all of you. Thank you very much.